Imagine a universe where traveling to distant stars takes mere moments instead of centuries. This is the tantalizing promise of faster-than-light travel, a concept that has captivated the minds of scientists, writers, and dreamers for generations. But what is the secret to achieving such incredible speeds? Is it merely a figment of science fiction, or could it one day become a reality? Today, we embark on a journey to explore the science behind faster-than-light travel and uncover the theories that might make it possible. To understand the possibility of faster-than-light travel, we first need to dive into the world of physics, particularly the theories of relativity introduced by Albert Einstein. According to special relativity, nothing can travel faster than the speed of light in a vacuum, a fundamental limit that seems to put a damper on our interstellar ambitions. However, the universe is full of surprises. General relativity, another of Einstein's groundbreaking theories, suggests that the fabric of space-time itself can be warped and curved. This has led to fascinating concepts like wormholes and warp drives, which could potentially allow us to bypass the speed limit set by special relativity. Wormholes, also known as Einstein-Rosen bridges, are theoretical passages through space-time that could create shortcuts for long journeys across the cosmos. Imagine folding a piece of paper and piercing it with a pencil. The pencil represents a wormhole connecting two distant points instantly. While wormholes sound like something out of a science fiction novel, scientists have been rigorously exploring their theoretical foundations. The challenge lies in the extreme conditions required to create and stabilize a wormhole, conditions that might involve exotic forms of matter and energy. Another exciting possibility comes from the concept of the warp drive, famously popularized by the Star Trek series. In 1994, physicist Miguel Alcubierre proposed a theoretical model where a spacecraft could achieve faster-than-light travel by contracting space in front of it and expanding space behind it, effectively surfing a wave of warped space-time. The warp drive concept, while speculative, has intrigued physicists because it doesn't violate the cosmic speed limit directly. Instead, it manipulates space-time itself, offering a potential loophole in the laws of physics. But the energy requirements for such a drive are currently beyond our technological capabilities. Quantum mechanics, the branch of physics dealing with the very small, also offers intriguing possibilities. Phenomena like quantum entanglement and tunneling suggest that information or particles might instantaneously influence each other over vast distances, hinting at potential methods for faster-than-light communication or travel. Then there are tachyons, hypothetical particles that always move faster than light. While their existence remains unproven, they represent another tantalizing clue in the puzzle of faster-than-light travel. If tachyons were found to exist, they could revolutionize our understanding of physics and open up new avenues for exploration. As we venture further into these scientific mysteries, it becomes clear that the journey to faster-than-light travel is fraught with challenges. Yet, each theory and discovery brings us one step closer to unlocking the secrets of the cosmos, and perhaps one day making the impossible possible. The idea of traveling through space has fascinated humanity long before modern science took shape. Ancient cultures often looked to the stars and imagined journeys to the heavens, inspiring myths and legends about gods and heroes traversing the cosmos. As we entered the age of reason and scientific inquiry, these early dreams began to take on more concrete forms. In the 17th century, astronomers like Johannes Kepler and Galileo Galilei laid the groundwork for understanding our place in the universe, speculating about the possibility of space travel. Kepler, in particular, was a visionary. He wrote letters to his peers discussing the concept of traveling to the moon, even suggesting the use of sails to harness the power of solar winds, an idea that echoes in modern solar sail technology. By the 19th century, the Industrial Revolution brought about technological advancements that fueled further speculation. Science fiction emerged as a genre, with authors like Jules Verne and H.G. Wells imagining voyages beyond Earth, sparking public interest and inspiring future scientists and engineers. Verne's From the Earth to the Moon depicted a manned projectile launched to the moon using a massive cannon. Though fantastical, Verne's work was grounded in the scientific knowledge of his time, blending imagination with emerging technological possibilities. H.G. Wells took a different approach in The War of the Worlds, exploring the idea of Martian invasions and the technology they might employ. While primarily a cautionary tale, Wells' work expanded the public's vision of what space travel and extraterrestrial life could entail. In the early 20th century, pioneers like Konstantin Tsiolkovsky began to lay the theoretical foundations for actual space travel. Tsiolkovsky, a Russian scientist, is often regarded as the father of astronautics. He proposed the use of rockets powered by liquid fuel, a concept that would become crucial for future space missions. Tsiolkovsky's famous equation, which calculates the change in velocity of a rocket, remains a cornerstone of rocket science. His visionary ideas included space stations, solar energy, and even colonizing other planets, far ahead of his time. Meanwhile, in the United States, Robert Goddard was making strides in practical rocketry. In 1926, he launched the world's first liquid-fueled rocket, a milestone that marked the beginning of modern rocketry and paved the way for space exploration. Goddard faced significant skepticism and ridicule from the public and his peers, but his relentless experimentation and success inspired future generations of rocket scientists, proving that space travel was more than just a dream. The interwar period saw the rise of groups dedicated to space travel, like the British Interplanetary Society and Germany's VFR, or Society for Space Travel. These organizations brought together enthusiasts and experts, fostering a community focused on turning science fiction into reality. In Germany, Wernher von Braun and his colleagues made significant advances in rocket technology, eventually leading to the development of the V-2 rocket during World War II. This technology, though initially used for warfare, would later become the basis for space exploration efforts in the post-war era. After the war, the captured German rocket technology and expertise were crucial in the space race between the United States and the Soviet Union. Both nations aimed to demonstrate their technological superiority through space exploration, leading to rapid advancements. In the Soviet Union, Sergei Korolev emerged as a key figure, overseeing the development of the R-7 rocket, which launched Sputnik, the world's first artificial satellite, in 1957. This achievement marked the beginning of the space age and a new era of human exploration. The early theories and efforts laid the groundwork for humanity's journey to the stars. They were driven by a combination of scientific curiosity, technological innovation, and an unyielding belief in the possibility of venturing beyond our planet. As we continue to explore the universe, we build upon the dreams and discoveries of these early pioneers. The development of the theory of relativity revolutionized our understanding of space, time, and the universe. At the dawn of the 20th century, physicists were grappling with anomalies in the behavior of light and the movement of objects, which classical mechanics couldn't explain. Albert Einstein, a young physicist working at the Swiss Patent Office, proposed a radical new idea in 1905. In his special theory of relativity, Einstein introduced the concept that the laws of physics are the same for all non-accelerating observers, and he stated that the speed of light in a vacuum is constant, regardless of the motion of the light source or observer. This theory led to the famous equation E=mc2, which describes the equivalence of energy and mass. It suggested that as objects move faster, they gain mass and require more energy to continue accelerating, making it impossible for any object with mass to reach the speed of light. Einstein's work on special relativity overturned long-standing notions of absolute space and time, showing that time can dilate and lengths can contract, depending on the relative motion of observers. This was a profound shift in our understanding of the universe's fundamental workings. Following this groundbreaking work, Einstein spent the next decade developing his general theory of relativity. Published in 1915, this theory extended his ideas to include gravity, proposing that massive objects cause a curvature in spacetime, which we perceive as gravity. General relativity provided a new framework for understanding gravitational phenomena, predicting phenomena such as the bending of light by gravity and the time dilation experienced near massive objects. These predictions have been confirmed by numerous experiments and observations. One of the most famous confirmations of general relativity came during the 1919 solar eclipse. Observations of starlight bending around the sun matched Einstein's predictions, bringing him international acclaim and solidifying the theory's acceptance within the scientific community. The implications of general relativity were far-reaching. It provided the foundation for modern cosmology, allowing scientists to model the structure and evolution of the universe, including the expansion of the universe and the existence of black holes. General relativity also introduced the concept of spacetime as a dynamic entity that can be warped and shaped by mass and energy. This led to the idea of wormholes, hypothetical tunnels through spacetime that could connect distant parts of the universe, potentially allowing for faster-than-light travel. Einstein's theories fundamentally changed our understanding of space and time, making them flexible and interconnected rather than rigid and absolute. This new perspective opened up a wealth of possibilities for theoretical physics and the exploration of the universe. In the decades following Einstein's work, physicists have continued to explore the implications of relativity. These efforts have included attempts to unify general relativity with quantum mechanics, leading to the development of quantum field theory and string theory. The ongoing quest to reconcile relativity with the quantum world has driven some of the most exciting research in modern physics, pushing the boundaries of our understanding and bringing us closer to a theory of everything that can describe all fundamental forces and particles. Relativity has also played a crucial role in advancing our technological capabilities. Technologies such as GPS rely on precise measurements of time and space, corrected for the effects of both special and general relativity to function accurately. As we continue to investigate the nature of the universe, the theories of relativity remain central to our scientific endeavors. They provide the framework for understanding phenomena on both the largest and smallest scales, from the motion of galaxies to the behavior of particles in accelerators. Einstein's legacy lives on in the ongoing exploration of space, time, and the fundamental laws of nature. His insights have not only deepened our comprehension of the universe, but have also paved the way for future discoveries and innovations that could one day make faster-than-light travel a reality. Einstein's special theory of relativity introduced a revolutionary idea: the speed of light as an absolute limit. This principle states that nothing can travel faster than the speed of light in a vacuum, which is approximately 299,192 kilometers per second, or about 186,282 miles per second. This speed limit arises from the way space and time are intertwined in the fabric of the universe. As an object approaches the speed of light, its mass effectively becomes infinite, and it requires an infinite amount of energy to move further, making faster-than-light travel impossible according to special relativity. The constancy of the speed of light means that all observers, regardless of their relative motion, measure the same speed for light. This concept challenges our everyday experiences, where speeds are additive. If you throw a ball while running, the ball's speed adds to your running speed. But light behaves differently. Einstein's equations show that as an object moves faster, time slows down for that object relative to a stationary observer. This time, dilation effect has been confirmed by numerous experiments, including those involving high-speed particles and precise atomic clocks on fast-moving aircraft. Length contraction is another consequence of approaching the speed of light. Objects moving at high speeds appear shorter along the direction of motion to a stationary observer. This effect, though not noticeable at everyday speeds, becomes significant as speeds approach the speed of light. One of the most profound implications of the light speed limit is its effect on causality. Faster-than-light travel or communication would violate the cause and effect relationship fundamental to our understanding of the universe, potentially allowing for paradoxes like sending information into the past. In practical terms, the speed of light limit affects everything from the transmission of signals across the cosmos to the design of future space missions. It sets a hard boundary on how quickly we can send information or travel between distant stars. Despite this limit, physicists continue to explore theoretical ways to circumvent it. Concepts like wormholes and warp drives are intriguing because they suggest methods to effectively bypass the speed limit by manipulating space-time itself, rather than moving through it faster than light. The light speed limit also plays a crucial role in the standard model of particle physics and the operation of particle accelerators. In these machines, particles are accelerated to speeds close to that of light, revealing fundamental properties of matter and energy. Einstein's insight into the speed of light as a cosmic speed limit has been confirmed by countless experiments and observations, forming one of the cornerstones of modern physics. Yet it also sparks our imagination, pushing us to find innovative solutions that could one day overcome this barrier. While the speed of light remains an insurmountable limit for objects with mass, it does not preclude the existence of phenomena or theoretical constructs that challenge our understanding. Tachyons, hypothetical particles that move faster than light, represent one such avenue of speculation, though they remain purely theoretical. The exploration of quantum mechanics has also opened new possibilities. Quantum entanglement, where particles influence each other instantaneously over vast distances, suggests that there may be aspects of the universe that transcend the classical light speed limit. However, these quantum phenomena do not violate relativity in the traditional sense, as they do not involve the transmission of information faster than light. They highlight the complex and often counterintuitive nature of the universe at the smallest scales. Einstein's speed of light limit forces us to think deeply about the nature of reality and the structure of the cosmos. It challenges our intuitions and drives scientific inquiry, leading to new theories and discoveries that continually reshape our understanding of the universe. The journey to faster-than-light travel may still be in the realm of science fiction, but the principles set forth by Einstein provide a foundation upon which future breakthroughs could be built. Exploring the limits of physics, we edge closer to unlocking the secrets of the universe and perhaps, one day, transcending the ultimate speed barrier. Science fiction has long captivated the public imagination with visions of faster-than-light travel. From the early works of Jules Verne and H.G. Wells to the modern tales of Star Trek and Star Wars, these stories have inspired generations to dream of journeys beyond our solar system. In the early 20th century, science fiction magazines like Amazing Stories and Astounding Science Fiction introduced readers to the concept of space travel. Writers like Isaac Asimov, Arthur C. Clarke, and Robert Heinlein wove intricate tales that made interstellar voyages seem within reach. Television and film have played a significant role in shaping our perceptions of faster-than-light travel. Star Trek, with its iconic warp drive, and Star Wars, with its hyperspace jumps, have presented compelling and visually stunning portrayals of what such travel might look like. These depictions often blend scientific principles with imaginative leaps, making the idea of faster-than-light travel both entertaining and thought-provoking. They provide a narrative framework that encourages viewers to consider the possibilities of space exploration. Public fascination with these stories has had a tangible impact on the scientific community. Many scientists and engineers have cited science fiction as a key inspiration for their careers, driving them to explore the frontiers of physics and engineering. The concept of faster-than-light travel in science fiction often involves advanced technologies and civilizations. These narratives prompt us to consider the technological advancements necessary to achieve such feats, sparking interest in fields like astrophysics, propulsion technology, and materials science. Beyond inspiring individual careers, science fiction has influenced public policy and funding for space exploration. The excitement generated by these stories helps build support for space programs and research initiatives, highlighting the importance of exploring beyond our planet. Science fiction also explores the philosophical and ethical implications of faster-than-light travel. Questions about the nature of time, the potential for encountering alien life, and the impact on human society are all common themes that provoke deeper reflection on our place in the universe. The imaginative worlds of science fiction offer a testing ground for ideas that might seem impossible or impractical today. By envisioning future technologies and societies, writers and filmmakers provide a canvas for exploring innovative solutions to real-world challenges. In many ways, science fiction serves as a cultural barometer, reflecting our hopes, fears, and aspirations regarding space travel. It captures the collective desire to push beyond the known and venture into the great unknown, a drive that is deeply embedded in the human spirit. The enduring popularity of science fiction ensures that new generations continue to be inspired by the possibilities of faster-than-light travel. As our understanding of the universe evolves, these stories adapt, incorporating the latest scientific discoveries and theories. By presenting faster-than-light travel as a tangible goal, science fiction helps maintain a sense of wonder and possibility. It keeps the dream of exploring distant galaxies alive, reminding us that the future is full of potential waiting to be realized. These narratives also encourage us to think critically about the challenges and obstacles that must be overcome to achieve faster-than-light travel. They highlight the importance of scientific research, collaboration, and perseverance in the face of seemingly insurmountable odds. In essence, science fiction acts as a bridge between imagination and reality, It connects the speculative with the scientific, offering a vision of what might be possible if we continue to push the boundaries of our knowledge and capabilities. As we continue to explore the mysteries of the universe, the influence of science fiction on our collective imagination remains a powerful force. It fuels our curiosity, drives our ambitions, and inspires us to reach for the stars, keeping the dream of faster-than-light travel alive and vibrant. As we transitioned from the imaginative worlds of science fiction to modern scientific theories, the quest for faster-than-light travel became a serious field of study. Researchers began to explore the fundamental principles of physics to see if such travel could be possible. Quantum mechanics emerged as a groundbreaking field, revealing the strange and counterintuitive behaviors of particles at the smallest scales. Concepts like quantum entanglement and tunneling suggested new ways to think about information transfer and movement through space. Quantum entanglement, where particles become instantly connected regardless of distance, hinted at the possibility of instantaneous communication, though it doesn't allow for faster-than-light travel directly. It challenges our classical understanding of spacetime and causality. Physicists also began to investigate the properties of spacetime itself, inspired by Einstein's general relativity. The idea that spacetime could be warped or curved opened up new possibilities for theoretical models that might allow for shortcuts through the cosmos. One of the most intriguing concepts to emerge was that of wormholes, hypothetical tunnels in spacetime that could connect distant regions of the universe. If such structures exist, they could potentially allow for travel that bypasses the speed of light limit. Theoretical physicist Kip Thorne and others have explored the mathematics of wormholes, considering the exotic matter and energy conditions that might be required to stabilize them. These studies remain speculative, but provide a fascinating avenue for future research. The idea of a warp drive, popularized by science fiction, also found its way into scientific discourse. Physicist Miguel Alcubierre proposed a theoretical model in 1994, suggesting that a spacecraft could achieve faster-than-light travel by distorting spacetime around it. Alcubierre's warp drive relies on creating a bubble of spacetime that moves faster than light, with the spacecraft inside this bubble. The concept requires enormous amounts of energy, particularly negative energy, which poses significant technological challenges. Despite these challenges, the warp drive remains an area of active research and speculation. Scientists are exploring the theoretical underpinnings and potential methods for generating the necessary energy, inspired by both scientific curiosity and the allure of interstellar travel. Dark energy and dark matter, mysterious components of the universe, also play a role in modern theories. Understanding these phenomena could unlock new insights into the structure of spacetime and the potential for manipulating it to achieve faster-than-light travel. Cosmologists study the expansion of the universe, driven by dark energy, to understand how the fabric of spacetime can be influenced on a cosmic scale. These insights might one day lead to breakthroughs in our ability to traverse vast distances quickly. As our understanding of the universe deepens, the interplay between quantum mechanics and general relativity remains a central challenge. The quest for a unified theory that reconciles these two pillars of physics could reveal new pathways for faster-than-light travel. String theory and other advanced theoretical frameworks aim to bridge this gap, offering potential explanations for the fundamental nature of reality. These theories propose extra dimensions and new particles that could play a role in enabling faster-than-light travel. Experimental physics also continues to push the boundaries of our knowledge. Particle accelerators, such as the Large Hadron Collider, probe the fundamental particles and forces that govern the universe, providing data that could inform future theories of faster-than-light travel. The journey from science fiction to scientific theory is ongoing, driven by a combination of imagination, curiosity, and rigorous research. Each new discovery brings us closer to understanding the true limits of our universe and the potential for transcending them. As we continue to explore these modern scientific theories, we keep the dream of faster-than-light travel alive. The transition from speculative fiction to plausible science is a testament to humanity's enduring desire to reach for the stars and explore the cosmos. Special relativity, introduced by Albert Einstein in 1905, fundamentally changed our understanding of space and time. This theory begins with two key postulates. First, the laws of physics are the same in all inertial frames of reference, meaning no particular frame is preferred over any other. Second, the speed of light in a vacuum is constant and independent of the motion of the light source or the observer. This constancy of light speed led to profound implications that challenged classical notions of absolute space and time. One of the most well-known consequences of special relativity is time dilation. According to this effect, time passes slower for an object moving at high speeds compared to an object at rest. This means that astronauts traveling at near light speeds would age more slowly than people on Earth. Another key result is length contraction. Objects moving at relativistic speeds appear shorter along the direction of motion to a stationary observer. This effect becomes significant only at speeds close to that of light and is imperceptible in everyday life. Mass-energy equivalence is perhaps the most famous outcome of special relativity, encapsulated in the equation E = mc2. This equation states that mass and energy are interchangeable, meaning a small amount of mass can be converted into a vast amount of energy. Special relativity also introduced the concept of simultaneity, showing that events that appear simultaneous to one observer may not be simultaneous to another, moving relative to the first. This relativity of simultaneity undermines the idea of a universal present moment, shared by all observers. These effects arise from the fact that space and time are not separate entities, but are interwoven into a single four-dimensional continuum known as spacetime. The coordinates of events in spacetime are dependent on the motion of the observer, leading to different perceptions of space and time. Special relativity has been confirmed by numerous experiments and observations, such as the behavior of particles in accelerators and the precise timing of clocks on fast-moving jets and satellites. These confirmations have solidified its status as a cornerstone of modern physics. The implications of special relativity extend beyond theoretical physics. Technologies such as GPS rely on relativistic corrections to function accurately, as the satellite's high speeds and varying gravitational fields affect the passage of time relative to observers on Earth. Despite its counterintuitive predictions, special relativity elegantly explains the observed behavior of light and matter at high speeds. It seamlessly integrates with Maxwell's equations of electromagnetism, providing a consistent framework for understanding the propagation of light. The development of special relativity also paved the way for general relativity, where Einstein extended his principles to include gravity and accelerated frames of reference. Together, these theories have revolutionized our understanding of the cosmos. Einstein's insights into the nature of space and time have had a lasting impact on science and philosophy. They challenge our perceptions and force us to rethink fundamental concepts that seem intuitive in our everyday experiences. Special relativity emphasizes the importance of perspective in measuring and observing the universe. It shows that our experiences of space and time are deeply connected to our state of motion, revealing a universe far more dynamic and interconnected than previously imagined. By fundamentally altering our understanding of space and time, special relativity has opened new avenues of research and exploration. It remains a vital area of study, inspiring physicists to delve deeper into the mysteries of the universe. As we continue to explore the frontiers of physics, the principles of special relativity will remain a guiding light, helping us navigate the complexities of the cosmos and pushing us toward new discoveries and technological advancements. The concept of the speed of light as a cosmic speed limit is a fundamental aspect of special relativity. According to Einstein's theory, the speed of light in a vacuum is the maximum speed at which all energy, matter, and information in the universe can travel. This speed limit arises from the structure of spacetime itself. When objects move closer to the speed of light, their mass effectively increases, requiring more and more energy to continue accelerating them. As they approach light speed, the energy required becomes infinite, making it impossible for any object with mass to reach, let alone exceed, this limit. Photons or particles of light travel at this maximum speed because they are massless. This constancy of light speed holds true regardless of the relative motion between the source of the light and the observer. This invariance is what leads to many of the counterintuitive predictions of special relativity. Time dilation is one such prediction. As an object's speed increases toward the speed of light, time for that object slows down relative to a stationary observer. This effect has been confirmed by experiments with high-speed particles and precision clocks, showing that time indeed passes differently at relativistic speeds. Length contraction is another consequence. Objects moving at speeds approaching the speed of light appear shorter along the direction of motion to a stationary observer. This phenomenon, though not noticeable at everyday speeds, becomes significant as velocities reach relativistic levels. The speed of light also plays a crucial role in the causality of events. It ensures that cause precedes effect, maintaining the logical sequence of events in the universe. If faster-than-light travel were possible, it could lead to paradoxes such as effects occurring before their causes. Despite the speed of light limit, the universe is still vast and mysterious. The light from distant stars and galaxies gives us a glimpse into the past, as the time it takes for light to travel these immense distances means we see these objects as they were millions or even billions of years ago. In practical terms, the speed of light limit affects our communication and exploration capabilities. Signals sent to distant spacecraft or planetary probes take time to reach their destinations and return, imposing a natural delay on our interactions with distant objects. This cosmic speed limit has profound implications for the possibility of interstellar travel. Current propulsion technologies, which are far slower than light speed, would take thousands of years to reach even the nearest stars. This limitation drives the quest for new propulsion methods that could one day bring us closer to achieving faster-than-light travel. Physicists have proposed various theoretical models to circumvent the speed of light limit, such as wormholes and warp drives. These ideas involve manipulating spacetime itself, rather than accelerating through it, to achieve effective faster-than-light travel. However, these concepts remain speculative and face significant scientific and technological hurdles. The speed of light as a cosmic speed limit also influences our understanding of the universe's expansion. The space between galaxies is expanding, with some regions moving away from us faster than the speed of light. This expansion doesn't violate relativity because it's the space itself that's growing, not the galaxies moving through space. Einstein's realization of the speed of light as an ultimate limit reshaped our understanding of the cosmos. It provided a foundation for the development of modern physics, influencing everything from the study of subatomic particles to the dynamics of galaxies and the large-scale structure of the universe. While the speed of light sets a hard limit on our current technological capabilities, it also sparks curiosity and drives innovation. Scientists continue to explore the fundamental principles of physics, seeking ways to push beyond our current boundaries and uncover new aspects of reality. As we advance our knowledge and technology, the cosmic speed limit challenges us to think creatively and explore alternative avenues for achieving our dreams of interstellar travel. The journey to overcome this limit is fueled by the human spirit's relentless drive to explore and understand the universe. Time dilation is one of the most intriguing consequences of Einstein's theory of relativity. This effect occurs when an object moves at a significant fraction of the speed of light, causing time to pass differently for the object in motion compared to a stationary observer. Imagine an astronaut traveling in a spacecraft at near light speeds. For the astronaut, time would pass normally within the spacecraft. However, to an observer on Earth, the astronaut's clock would appear to tick more slowly. This means that if the astronaut's journey lasted 5 years on their clock, much more time could have passed on Earth. This effect has been confirmed through various experiments. One famous test involved precise atomic clocks placed on fast-moving airplanes. After the flights, the clocks on the planes showed slightly less elapsed time than identical clocks that remained stationary, consistent with predictions from relativity. Time dilation also occurs in the presence of strong gravitational fields, as predicted by general relativity. Near massive objects like black holes, the intense gravitational pull can slow down time relative to areas with weaker gravitational fields. This phenomenon is often depicted in science fiction, such as in the movie Interstellar. GPS satellites orbiting Earth provide a practical example of time dilation at work. These satellites move at high speeds and experience less gravitational pull compared to objects on Earth's surface. Engineers must account for the resulting time differences to ensure the system's accuracy, demonstrating the real-world relevance of relativistic effects. In theoretical scenarios involving near-light-speed travel, time dilation offers a potential method for future interstellar journeys. Astronauts traveling at such speeds could reach distant stars within their lifetimes, although thousands of years might pass on Earth during their voyage. Time dilation challenges our everyday experiences and intuitive understanding of time. It reveals that time is not a fixed and universal constant, but a flexible dimension that can be stretched or compressed, depending on relative motion and gravitational forces. This relativistic effect also impacts our understanding of the universe's lifespan and the life cycles of stars and galaxies. For instance, particles called muons, produced by cosmic rays striking Earth's atmosphere, live much longer when moving at high speeds, reaching the surface before decaying. In the realm of particle physics, time dilation allows high-energy particles in accelerators to exist longer than they would at rest, providing scientists with the opportunity to study their properties and interactions in greater detail. The implications of time dilation extend to the theoretical possibility of time travel. While traveling forward in time at an accelerated rate is feasible through near-light speed travel, reversing time or traveling to the past presents more complex challenges and paradoxes. Time dilation also raises philosophical questions about the nature of reality and our perception of time. It challenges the notion of an absolute present, suggesting instead that the flow of time is relative and dependent on one's frame of reference. Understanding time dilation is crucial for astrophysics and cosmology, as it influences the behavior of objects in extreme environments, such as neutron stars and black holes. It also plays a role in the dynamics of high-energy astronomical phenomena. Despite its counterintuitive nature, time dilation is a well-established and experimentally verified aspect of relativity. It underscores the interconnectedness of space and time, shaping our modern understanding of the universe's fundamental structure. As we continue to explore the cosmos and develop technologies that push the limits of speed and gravity, time dilation remains a central consideration in both theoretical research and practical applications. Its effects remind us that the universe operates on principles that often defy our everyday experiences, pushing us to expand our horizons and deepen our comprehension of reality. Length contraction is another fascinating prediction of Einstein's theory of relativity. According to this effect, objects moving at relativistic speeds will appear shorter along the direction of motion to a stationary observer. Consider a spaceship traveling close to the speed of light. To an observer on Earth, the spaceship would appear compressed in the direction of its travel, while its width and height remain unchanged. For the crew aboard the spaceship, however, nothing would seem different about their dimensions. This phenomenon, like time dilation, becomes significant only at speeds approaching that of light. At everyday speeds, the effects are negligible and go unnoticed in our daily experiences. The degree of length contraction depends on the object's velocity relative to the speed of light. The faster the object moves, the more pronounced the contraction becomes. This relationship is described by the Lorentz factor, which quantifies the amount of contraction experienced. Length contraction and time dilation are both manifestations of the same underlying principles in special relativity. They illustrate how measurements of space and time vary depending on the relative motion of observers. An important implication of length contraction is its effect on the structure of particles at high speeds. In particle accelerators, particles moving at relativistic speeds experience contraction, affecting how they interact and collide, providing insights into fundamental physics. Length contraction has also been confirmed experimentally, particularly through observations of particles moving close to light speed. These experiments validate the predictions made by relativity and demonstrate the tangible impact of this phenomenon. Understanding length contraction helps us comprehend the relativistic nature of the universe. It challenges our classical intuition and reveals the dynamic interplay between space and time at high velocities. In theoretical scenarios of near light speed travel, length contraction would significantly alter perceptions of distance. A journey that seems immense to a stationary observer might appear much shorter to someone traveling at relativistic speeds. This effect raises intriguing possibilities for future space exploration. If humanity ever develops the technology for near light speed travel, length contraction could make interstellar distances more manageable from the perspective of the travelers. Length contraction also contributes to our understanding of high-energy astrophysical phenomena. Objects moving at relativistic speeds, such as jets emitted by black holes, exhibit this effect, influencing their observed properties and behaviors. The interplay between length contraction and time dilation emphasizes the relativity of simultaneity. Events that occur simultaneously in one frame of reference may not be simultaneous in another, highlighting the flexible nature of space-time. Despite its abstract nature, length contraction has practical implications for modern technology and research. It informs the design and operation of high-speed particle detectors and the analysis of cosmic ray interactions. So, as we push the boundaries of our understanding of the universe, length contraction remains a key concept in relativity. It underscores the importance of considering relativistic effects in both theoretical and experimental physics. Length contraction, along with time dilation, reshapes our perception of reality. It reveals a universe where space and time are not fixed and absolute, but are fluid and relative, depending on the motion of the observer. These insights continue to inspire and challenge our pursuit of knowledge and exploration. The implications of relativity for faster-than-light travel are profound and challenging. Einstein's theory sets the speed of light as an absolute limit, which poses significant hurdles for achieving faster-than-light travel with current understanding. One major implication is the enormous energy requirement. As an object approaches the speed of light, its mass increases exponentially, necessitating an infinite amount of energy to reach or surpass light speed. This makes conventional faster-than-light travel seem impossible with known technology. Time dilation and length contraction also complicate the picture. Near light speed travel would lead to significant time discrepancies between travelers and those left behind. While this offers interesting possibilities for long-term space missions, it creates practical and emotional challenges. The concept of causality is another critical factor. Faster-than-light travel could potentially lead to causality violations, where effects precede causes. This paradox undermines the logical structure of physical laws and challenges our understanding of time. One proposed solution involves using wormholes. These theoretical passages through space-time could connect distant points instantaneously, effectively allowing faster-than-light travel without breaking the speed limit locally. However, creating and stabilizing wormholes would require exotic matter with negative energy, a substance not yet proven to exist. Warp drive technology is another intriguing concept. By manipulating space-time itself, a warp drive could create a bubble where space contracts in front of a spacecraft and expands behind it. This method bypasses the need for faster-than-light travel within the bubble, but the energy demands and physical feasibility remain speculative. Quantum mechanics introduces phenomena like quantum entanglement, where particles affect each other instantaneously over large distances. While not a means of faster-than-light travel, it suggests that aspects of the universe operate beyond classical limits, offering potential insights for future breakthroughs. Tachyons, hypothetical particles that always travel faster than light, present another avenue of exploration. If tachyons exist, they could revolutionize our understanding of physics and open new possibilities for faster-than-light travel. However, their existence remains unproven and controversial. General relativity's insights into space-time curvature suggest that manipulating gravitational fields might offer paths to faster-than-light travel. Concepts like the Alcubierre drive explore how space-time could be warped to achieve effective faster-than-light travel without violating relativity's constraints. Dark energy and dark matter, the mysterious components of the universe, could hold keys to faster-than-light travel. Understanding their properties and how they influence space-time might reveal new methods for traversing the cosmos more quickly than light permits. Theoretical physics continues to explore these and other possibilities, pushing the boundaries of our understanding. While practical faster-than-light travel remains elusive, these studies contribute to our broader knowledge of the universe and its fundamental laws. Advanced propulsion technologies, such as ion drives and antimatter engines, aim to increase travel speeds within the framework of relativity. Though not offering faster-than-light capabilities, they represent steps toward more efficient and faster space travel. Practical challenges, including the need for life support and protection from cosmic radiation, also play a crucial role in developing faster-than-light travel. Any viable method must address these issues to ensure the safety and viability of long-duration space missions. Public interest and investment in space exploration drive the ongoing research into faster-than-light travel. As our technological capabilities advance, the pursuit of these ambitious goals continues to inspire scientists, engineers, and enthusiasts worldwide. The dream of faster-than-light travel remains a powerful motivator. It pushes the limits of human ingenuity and challenges us to explore the unknown. While current physics sets stringent limits, The quest to overcome these barriers is an enduring testament to our desire to reach the stars and beyond. General relativity, proposed by Albert Einstein in 1915, extends the principles of special relativity to include gravity. It provides a new way of understanding how matter and energy influence the fabric of spacetime. At the heart of general relativity is the concept that gravity is not a force in the traditional sense. Instead, it's the result of the curvature of spacetime caused by mass and energy. Objects move along the paths defined by this curvature. Einstein's field equations describe how matter and energy determine the curvature of spacetime. These equations are complex, but they fundamentally link the distribution of mass and energy to the geometric properties of spacetime. One of the most famous predictions of general relativity is the bending of light by gravity. This phenomenon, known as gravitational lensing, occurs when light from a distant star is bent around a massive object, like a galaxy or a black hole, creating multiple images or arcs of the star. Another key prediction is the existence of black holes, regions of spacetime where gravity is so intense that not even light can escape. The event horizon of a black hole marks the boundary beyond which nothing can return. General relativity also predicts the phenomenon of time dilation in strong gravitational fields. Clocks closer to a massive object, like a planet or a star, run slower compared to those further away. This has been confirmed by experiments involving precise measurements of time at different altitudes. The theory revolutionized our understanding of the universe's structure and dynamics. It provided the foundation for modern cosmology, including the study of the Big Bang and the expansion of the universe. Gravitational waves are another remarkable prediction of general relativity. These ripples in spacetime are caused by violent astrophysical events, such as the merging of black holes or neutron stars. The first direct detection of gravitational waves in 2015 confirmed Einstein's prediction and opened a new era of observational astronomy. General relativity's implications extend to the Global Positioning System, or GPS. The satellites in the GPS network must account for the effects of both special and general relativity to provide accurate positioning information. Einstein's theory also influences our understanding of time travel. While forward time travel is supported by the relativistic effects of time dilation, traveling back in time involves solutions to the equations of general relativity that are highly speculative and involve exotic conditions. The theory has stood up to rigorous testing over the past century. From the precession of Mercury's orbit to the precise tracking of spacecraft, general relativity consistently provides accurate predictions that match observations. General relativity challenges our intuitions about space and time, showing that they are dynamic and intertwined rather than fixed and absolute. It introduces a four-dimensional spacetime where gravity can bend the paths of objects and the flow of time. The success of general relativity has inspired ongoing research into unifying it with quantum mechanics. This quest for a theory of quantum gravity aims to reconcile the behavior of the very large, governed by general relativity, with the behavior of the very small, described by quantum mechanics. Black holes, as predicted by general relativity, have become key objects of study in understanding extreme gravitational environments. Observations of black hole mergers in the event horizon provide critical tests of the theory. General relativity continues to shape our exploration of the universe. It remains a cornerstone of modern physics, guiding our understanding of everything from the motion of planets to the evolution of galaxies and the ultimate fate of the cosmos. The concept of space-time curvature is central to general relativity. Unlike Newtonian gravity, which views gravity as a force between masses, general relativity describes it as the result of curved space-time. Imagine spacetime as a two-dimensional rubber sheet. When a heavy object, like a planet or a star, is placed on this sheet, it creates a depression or a curve. Smaller objects, like satellites or comets, move along the curves created by the larger mass. This curvature affects the paths that objects take. In the absence of other forces, objects follow the straightest possible paths in this curved spacetime, known as geodesics. This is why planets orbit stars and moons orbit planets. Spacetime curvature is described mathematically by the Einstein field equations. These equations relate the amount of mass and energy present to the curvature of spacetime, showing how they influence one another. One dramatic example of spacetime curvature is a black hole. Here, the curvature becomes so steep that nothing, not even light, can escape from within a certain radius known as the event horizon. Inside this horizon, the path of every object inevitably leads towards the center. Gravitational lensing, where light from distant stars is bent around massive objects like galaxies or black holes, provides visual evidence of space-time curvature. This effect allows astronomers to observe objects otherwise hidden behind massive structures. The curvature of space-time also explains the phenomenon of gravitational time dilation. Clocks closer to a massive object, which experiences stronger gravitational pull, tick more slowly compared to those further away. This effect has been confirmed by experiments and is crucial for the accuracy of GPS technology. Space-time curvature is not just a theoretical concept, it has practical implications. For example, the precise calculations needed for satellite navigation systems must account for the curvature of space-time around Earth to provide accurate positioning data. The study of space-time curvature has led to the discovery of phenomena like wormholes, hypothetical bridges connecting distant points in space-time. If they exist, wormholes could theoretically allow for faster-than-light travel by providing shortcuts through space-time. Space-time curvature is dynamic and evolves with the distribution of mass and energy. This dynamic nature is evident in cosmological models, where the universe's expansion affects the overall curvature of space-time on a cosmic scale. Curvature is not restricted to large scales. On small scales, near massive particles, space-time can be incredibly curved. This extreme curvature is what makes studying black holes and neutron stars so fascinating, as they provide natural laboratories for testing general relativity. Understanding space-time curvature helps explain the motion of galaxies and the structure of the universe. It provides insights into the behavior of cosmic phenomena and underpins many aspects of modern astrophysics. The concept also plays a crucial role in gravitational wave astronomy. Gravitational waves, ripples in space-time caused by accelerating masses such as merging black holes, stretch and squeeze space-time as they propagate, providing a new way to observe and understand the universe. Space-time curvature influences the formation and evolution of structures in the universe. From the bending of light around galaxies to the dynamics of galaxy clusters, its effects are ubiquitous and fundamental to our understanding of cosmic phenomena. This curvature is integral to the ongoing efforts to unify general relativity with quantum mechanics. Understanding how space-time behaves at the smallest scales and highest energies remains one of the greatest challenges in theoretical physics. The exploration of space-time curvature continues to expand our knowledge of the universe. It shapes our understanding of everything from the orbits of planets to the evolution of galaxies and the ultimate fate of the cosmos, providing a deeper appreciation of the intricate and dynamic nature of space-time. Einstein-Rosen bridges, commonly known as wormholes, are theoretical passages through space-time. They were first proposed by Albert Einstein and Nathan Rosen in 1935 as solutions to the equations of general relativity. A wormhole can be visualized as a tunnel connecting two separate points in space-time. If such structures exist, they could potentially allow for faster-than-light travel by providing shortcuts between distant regions of the universe. In the simplest form, a wormhole consists of two mouths connected by a throat. The mouths are the entry and exit points, while the throat is the passage through which matter and information could travel. Theoretical physicists have explored various types of wormholes. Some are traversable, meaning that objects could pass through them, while others are non-traversable, existing only as theoretical constructs without practical application for travel. For a wormhole to be stable and traversable, it would require exotic matter with negative energy density. This exotic matter would keep the wormhole open and prevent it from collapsing, but such matter has not yet been discovered or created in sufficient quantities. Traversable wormholes are an exciting concept because they could theoretically connect distant regions of space-time instantaneously. This means that a journey across vast cosmic distances could take a matter of moments, circumventing the speed of light limit. The concept of wormholes has captured the imagination of science fiction writers and filmmakers. Stories often depict wormholes as gateways to other galaxies, parallel universes, or different points in time, providing endless narrative possibilities. Wormholes also raise fascinating questions about the nature of causality and the potential for time travel. If one end of a wormhole moves relative to the other, It could theoretically create time loops or allow travel into the past. While wormholes are a compelling theoretical idea, creating and stabilizing one would require technology and materials far beyond our current capabilities. The energy requirements alone would be astronomical, involving negative energy and advanced control over space-time. Despite these challenges, the study of wormholes continues to be a rich field of theoretical physics. Researchers explore the mathematical properties and potential implications of these structures, pushing the boundaries of our understanding of the universe. Observationally detecting a wormhole, if they exist, would be an extraordinary achievement. Scientists speculate that certain gravitational wave signatures or unusual gravitational lensing effects could hint at the presence of a wormhole. Some theories suggest that naturally occurring wormholes could exist in the universe, perhaps within the dense cores of black holes or as remnants from the early universe. These natural wormholes might be incredibly small or hidden within complex gravitational fields. In addition to theoretical work, advanced simulations help scientists explore the dynamics and stability of wormholes. These simulations provide insights into how such structures might form, behave, and interact with matter and energy. The idea of using wormholes for interstellar travel remains speculative, but it fuels ongoing research into the fundamental nature of space-time. Understanding wormholes could unlock new principles of physics and potentially revolutionize our approach to space exploration. Einstein-Rosen bridges embody the adventurous spirit of theoretical physics. They challenge our perceptions of space, time, and reality, inviting us to imagine new possibilities for travel and connection across the cosmos. As research progresses, wormholes continue to inspire scientists and the public alike with the promise of unprecedented discoveries. The theoretical feasibility of wormholes is a topic of intense debate and exploration among physicists. While general relativity predicts the existence of these structures, numerous challenges must be overcome to determine if they can exist in a stable, traversable form. One of the main issues is the requirement for exotic matter. This type of matter would need to have negative energy density, which is necessary to keep a wormhole open. In classical physics, all known forms of matter have positive energy density, making exotic matter a purely theoretical construct at this point. Quantum field theory suggests that negative energy densities might be possible under certain conditions, such as the Casimir effect. However, generating and sustaining sufficient negative energy to stabilize a wormhole would require technological advancements far beyond our current capabilities. Another challenge is the stability of wormholes. Without exotic matter, a wormhole would collapse almost instantaneously after formation, making it impossible for anything to traverse it. Theoretical models show that even minor perturbations could cause a wormhole to pinch off and close. The equations of general relativity allow for the existence of wormholes, but they do not provide guidance on how to create or sustain them. This leaves researchers to explore speculative scenarios and advance theoretical frameworks to address these gaps. The energy conditions required for wormholes involve manipulating space-time in ways that are currently beyond our understanding. Achieving this would likely involve a new era of physics, potentially including a unified theory that merges general relativity with quantum mechanics. Some theories propose that wormholes could form naturally in the early universe, during the inflationary period. These primordial wormholes might still exist today, hidden within the vast expanses of spacetime. Detecting such wormholes, however, remains a significant challenge. Gravitational waves, ripples in spacetime caused by massive objects accelerating, could potentially provide indirect evidence of wormholes. Unusual patterns or anomalies in gravitational wave data might hint at the presence of these enigmatic structures. The search for wormholes also extends to astrophysical phenomena. Certain features in the dynamics of black holes, such as peculiarities in their event horizons or unusual radiation signatures, could indicate the influence of a wormhole. If wormholes do exist, they might also be connected to the mysterious dark matter and dark energy that make up most of the universe's mass and energy. Understanding these connections could provide insights into both wormholes and the broader structure of the cosmos. Advanced computer simulations play a crucial role in studying the theoretical feasibility of wormholes. These simulations allow physicists to model the complex interactions and stability conditions of hypothetical wormholes under various scenarios. The potential applications of stable, traversable wormholes are vast and transformative. They could revolutionize space travel, allowing for instant connections between distant regions of the universe. This could make interstellar exploration and colonization feasible within human lifetimes. Despite the speculative nature of wormholes, the pursuit of their theoretical feasibility drives progress in fundamental physics. Exploring these ideas pushes the boundaries of what we know about spacetime, gravity, and the fundamental forces of nature. The challenges are immense, but the rewards of discovering or creating a traversable wormhole would be unparalleled. It would open new frontiers for science and exploration, fundamentally changing our understanding of the universe. As research continues, the theoretical feasibility of wormholes remains an open question. It represents one of the most exciting and profound areas of inquiry in modern physics, promising to keep scientists engaged in the quest for answers to some of the universe's deepest mysteries. Exploring the potential of wormholes brings numerous challenges and limitations. First, the requirement for exotic matter with negative energy density remains a significant obstacle. Without this, maintaining a stable, traversable wormhole is currently impossible according to our understanding of physics. Another limitation is the sheer scale of energy required. Even if exotic matter could be harnessed, the amount needed to stabilize a wormhole would be astronomical, far exceeding our current or foreseeable energy production capabilities. The stability of wormholes is also a critical issue. Theoretical models suggest that even the slightest disturbance could cause a wormhole to collapse. This instability poses a major challenge for any practical application involving travel through wormholes. Time dilation effects within the throat of a wormhole could create additional complications. These effects might differ significantly from those experienced outside the wormhole, potentially causing severe temporal dislocations for travelers. The entry and exit points, mouths of a wormhole, could be subjected to intense gravitational forces. These forces could potentially damage or destroy any spacecraft or object attempting to traverse the wormhole. Navigating through a wormhole presents its own set of difficulties. Precise control over entry and exit points would be essential to avoid emerging in hazardous regions of space, such as near a black hole or inside a star. Even if a stable wormhole could be created, shielding travelers from intense gravitational forces and radiation within the wormhole would be necessary. Current technology lacks the means to provide such protection. There is also the issue of wormhole size. Theoretical models suggest that naturally occurring wormholes, if they exist, might be microscopic. Expanding these to a size that could accommodate spacecraft would require breakthroughs in our understanding of space-time manipulation. Theoretical solutions often involve highly speculative physics, such as manipulating higher dimensions or utilizing advanced quantum field effects. These areas remain largely unexplored and are not well understood. Another challenge is detecting and confirming the existence of wormholes. Without clear evidence, much of the theoretical work remains speculative, making it difficult to secure the necessary resources and funding for further research. Practical experimentation with wormholes is currently beyond our reach. Most studies rely on complex mathematical models and computer simulations, which, while informative, cannot substitute for empirical data. There are also philosophical and ethical considerations. The potential to create shortcuts through space-time raises questions about the consequences for causality and the fundamental structure of the universe. Interference with the natural fabric of space-time could have unforeseen consequences, potentially destabilizing local or even cosmic structures. The risks involved must be thoroughly understood and mitigated. Legal and political challenges would also arise with the advent of wormhole technology. The ability to travel instantaneously across vast distances could lead to disputes over territorial sovereignty and the regulation of interstellar travel. Despite these formidable challenges and limitations, the pursuit of wormhole research continues to inspire scientists. Addressing these obstacles requires interdisciplinary collaboration, innovative thinking, and a willingness to explore the frontiers of physics. Each step forward brings us closer to understanding the true potential and limitations of these fascinating theoretical constructs. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, offers a fascinating theoretical approach to faster-than-light travel. Unlike traditional propulsion, it involves manipulating space-time itself to achieve effective faster-than-light speeds. The concept relies on creating a warp bubble around a spacecraft. Inside this bubble, Spacetime contracts in front of the spacecraft and expands behind it, effectively allowing the spacecraft to move faster than light relative to an outside observer. This method circumvents the light speed limit because the spacecraft itself doesn't move through spacetime in the conventional sense. Instead, the bubble of warped spacetime carries the spacecraft along, much like a surfer riding a wave. The Alcubierre drive's theoretical foundation lies in the equations of general relativity. These equations show that such a warp bubble is mathematically possible, although creating and sustaining one presents significant challenges. One of the major hurdles is the requirement for exotic matter with negative energy density. This exotic matter is necessary to generate the warp bubble and maintain its structure. However, like with wormholes, negative energy density remains purely theoretical at this point. The energy requirements for an Alcubierre drive are also astronomical. Initial estimates suggested that the energy equivalent to the mass of Jupiter would be needed to create a small warp bubble. Later refinements have reduced this estimate, but the required energy remains far beyond our current capabilities. Another challenge is controlling the warp bubble. The drive would need to precisely manipulate spacetime, ensuring the bubble remains stable and directed towards the desired destination. Any instability could have catastrophic consequences for the spacecraft and its occupants. There's also the issue of causality and potential time paradoxes. Since the Alcubierre drive involves faster-than-light travel, it could theoretically lead to situations where cause and effect are reversed, posing significant challenges to our understanding of physics. The concept of the Alcubierre drive has inspired a great deal of scientific and popular interest. It has been featured in numerous science fiction stories, often as a plausible method for interstellar travel, fueling public imagination and curiosity. Despite the challenges, research into the Alcubierre drive continues. Scientists explore ways to reduce the energy requirements and better understand the properties of negative energy density, hoping to bring the concept closer to practical feasibility. Experimental investigations into related phenomena, such as the Casimir effect, offer insights into the properties of negative energy. These studies are crucial for understanding whether the exotic matter required for a warp drive could exist. Computer simulations and advanced mathematical models play a key role in this research. They allow scientists to explore the behavior of warp bubbles under various conditions, providing valuable data on stability and energy requirements. If the Alcubierre drive could be realized, it would revolutionize space travel. Journeys to distant stars that would take thousands of years with conventional technology could be completed in mere moments, opening up the cosmos for exploration and colonization. The drive also raises ethical and philosophical questions. The ability to traverse vast distances instantaneously would have profound implications for human society, culture, and our understanding of our place in the universe. While the Alcubierre drive remains speculative, it exemplifies the spirit of scientific inquiry and the quest to push the boundaries of what is possible. It challenges us to think beyond our current limitations and envision a future where the stars are within our reach. A warp drive works by distorting the fabric of spacetime around a spacecraft. Instead of moving the spacecraft through space at high speeds, the warp drive manipulates spacetime itself to create a bubble that carries the spacecraft along. This bubble is known as a warp bubble. In front of the bubble, spacetime contracts, pulling the destination closer. Behind the bubble, spacetime expands, pushing the starting point away. This process allows the spacecraft to effectively travel faster than light without breaking the speed limit within the bubble. The spacecraft sits in a region of flat spacetime inside the warp bubble. It remains stationary relative to the bubble, experiencing none of the relativistic effects associated with near light speed travel, such as time dilation or length contraction. The creation of a warp bubble requires exotic matter with negative energy density. This exotic matter generates the necessary spacetime distortions to form and sustain the bubble. However, negative energy is still a theoretical concept, with no practical means of production or manipulation currently available. Energy requirements are a significant challenge for a warp drive. Initial calculations suggested enormous amounts of energy, comparable to the mass energy of entire planets. Recent refinements have reduced these estimates, but the energy needed remains beyond current technological capabilities. Controlling the warp bubble is another critical aspect. The drive must be able to precisely generate and direct the bubble, ensuring it maintains stability and moves towards the intended destination. Any instability could cause the bubble to collapse, potentially endangering the spacecraft and its crew. The warp drive must also address the issue of debris and obstacles in space. A traditional spacecraft can maneuver to avoid collisions, but a warp bubble moving faster than light would encounter particles and radiation that could pose significant hazards. One proposed solution is a deflector shield to clear the path ahead of the warp bubble. This shield would need to be incredibly powerful and sophisticated to protect the spacecraft from high-energy particles and other space debris. Another consideration is the effect of a warp bubble on the surrounding environment. The creation and movement of the bubble could generate intense gravitational waves or other disturbances, potentially affecting nearby objects or systems. The drive must also consider the entry and exit points of the warp bubble. Transitioning from normal spacetime to the distorted spacetime within the bubble, and vice versa, requires precise control to ensure smooth and safe passage. Navigating a warp drive presents unique challenges. Traditional navigation relies on celestial landmarks and precise measurements of distance and velocity. A warp drive would need a new navigation system to account for the space-time distortions it creates. Despite these challenges, the theoretical foundation of a warp drive offers an exciting possibility for interstellar travel. If these issues can be addressed, a warp drive could enable humans to explore distant stars and galaxies within a human lifetime. The concept of a warp drive continues to inspire researchers, science fiction writers, and the public. It represents the ultimate goal of space exploration, pushing us to expand our technological capabilities and deepen our understanding of the universe. As our knowledge of physics and technology advances, the dream of a functional warp drive becomes a symbol of human ingenuity and our enduring desire to reach for the stars. The energy requirements for a warp drive are staggering and remain one of the most daunting challenges in realizing this technology. Theoretical calculations suggest that vast amounts of energy would be necessary to manipulate spacetime on the scale required for faster-than-light travel. The concept hinges on the creation of a warp bubble, which would involve generating intense gravitational fields and warping space-time itself. Such manipulation demands energy densities far beyond anything currently achievable. Early estimates propose that the energy equivalent to the mass of Jupiter would be needed to create a small, stable warp bubble. While subsequent refinements have lowered these estimates somewhat, the energy requirements still far exceed any practical energy source known to science. The energy needed for a warp drive is not just about raw power, but also about the specific properties of that energy. It would need to be precisely directed and controlled to create and maintain the warp bubble without causing catastrophic effects to the spacecraft or its surroundings. One possible source of energy for a warp drive could be matter-antimatter annihilation. This process converts mass directly into energy with high efficiency, but harnessing and containing antimatter poses significant technical challenges. Other speculative energy sources, such as zero-point energy or vacuum energy, are also considered. These hypothetical energy reservoirs exist at the quantum level, but tapping into them requires a profound understanding of quantum physics and technology that does not yet exist. The search for novel energy solutions for a warp drive is closely tied to advancements in theoretical physics and engineering. Breakthroughs in understanding exotic forms of energy and their manipulation could pave the way towards making warp drive technology a reality. Another approach involves reducing the energy requirements through optimization and innovation. Research focuses on refining the theoretical models of warp drive operation to identify potential energy-saving strategies. Efforts are also underway to explore alternative propulsion methods that could complement or enhance the capabilities of a warp drive. These include advanced ion propulsion systems, nuclear propulsion, and even concepts like solar sails for long-distance travel. Theoretical studies continue to refine our understanding of the energy dynamics involved in creating and sustaining a warp bubble. This research is crucial for evaluating the feasibility of warp drive technology and identifying viable paths forward. The feasibility of a warp drive ultimately depends on our ability to overcome these energy challenges. Advancements in energy generation, storage, and conversion technologies will be essential for making progress towards achieving faster-than-light travel. The quest for a practical warp drive inspires collaboration among physicists, engineers, and technologists worldwide. It represents a frontier of scientific inquiry that pushes the boundaries of our understanding of physics and the universe. Addressing the energy requirements for a warp drive involves interdisciplinary research across multiple fields of science and engineering. It requires innovative thinking and the willingness to explore unconventional ideas and approaches. While the challenges are formidable, the potential rewards of developing a warp drive are immense. Beyond enabling interstellar travel, warp drive technology could revolutionize space exploration and our understanding of the cosmos. The pursuit of a warp drive also fuels public imagination and interest in science and space exploration. It captures the spirit of exploration and discovery that drives humanity's quest to explore the unknown and expand our horizons. The energy requirements for a warp drive represent a critical hurdle in realizing this revolutionary technology. Overcoming these challenges will require breakthroughs in energy science, engineering, and theoretical physics. But the potential benefits make the pursuit worthwhile. The energy requirements for a warp drive are one of the most daunting challenges in making this theoretical technology a reality. Initially, calculations suggested that creating a warp bubble would require an amount of energy equivalent to the mass energy of Jupiter, which is far beyond our current capabilities. This enormous energy requirement stems from the need to generate and sustain the negative energy density required to form and maintain the warp bubble. Negative energy is necessary to create the spacetime distortions that allow the warp bubble to move through spacetime effectively. Recent theoretical advancements have reduced these initial energy estimates significantly. Some researchers have proposed modifications to the original Alcubierre drive concept, such as altering the shape of the warp bubble, which could potentially lower the energy requirements by several orders of magnitude. Despite these reductions, the energy required remains immense. Even the most optimistic estimates suggest that the energy needed is still far beyond what our most powerful current or near-future technologies can produce. One proposed source of the vast amounts of energy needed is antimatter. Antimatter reactions release energy far more efficiently than chemical or nuclear reactions. However, producing and storing antimatter in the quantities required for a warp drive presents its own set of challenges. Another potential source is harnessing the energy of vacuum fluctuations, also known as zero-point energy. This concept involves tapping into the energy present in empty space due to quantum fluctuations. While theoretically possible, practical methods to harness zero-point energy are still purely speculative. Fusion power, another promising technology, could potentially provide the high energy outputs needed. Advances in fusion research aim to create sustainable and controlled fusion reactions, which could eventually provide a powerful and long-term energy source for various applications, including a warp drive. Some scientists suggest that future civilizations could harness the energy of entire stars or even galaxies. Dyson spheres, hypothetical megastructures that surround a star to capture its energy output, represent one such futuristic concept. However, constructing such structures is well beyond our current technological capabilities. The challenge of containing and directing this vast energy is another critical aspect. The systems used to generate and sustain the warp bubble would need to handle extreme energy densities without succumbing to catastrophic failure. Additionally, the transition from theoretical energy sources to practical engineering solutions involves overcoming numerous technical hurdles. The development of materials that can withstand the extreme conditions inside a warp drive is just one of the many engineering challenges. Managing the heat generated by the warp drive's energy systems is also crucial. Without efficient heat dissipation methods, the spacecraft and its components could overheat, leading to potential failure. Energy storage solutions must also be advanced. Current energy storage technologies, such as batteries and capacitors, are inadequate for the scale required by a warp drive. New storage methods capable of holding and rapidly discharging enormous amounts of energy are necessary. Energy conversion efficiency is another factor. Any warp drive system would need to convert stored or generated energy into the necessary form to create and sustain the warp bubble with minimal loss. Exploring these energy challenges pushes the boundaries of our scientific understanding and engineering capabilities. Each step forward in energy research brings us closer to potentially realizing the dream of faster-than-light travel. While the energy requirements for a warp drive are currently insurmountable, The pursuit of solutions drives innovation across multiple fields. Future breakthroughs in energy generation, storage, and conversion could eventually make the seemingly impossible a reality. Current research and developments in the field of faster-than-light travel, particularly focusing on the warp drive concept, are ongoing and multifaceted. While practical warp drive technology remains a distant goal, theoretical and experimental work continues to advance our understanding. One major area of research involves refining the mathematical models of the warp drive. Scientists are exploring different configurations of the warp bubble to minimize energy requirements and enhance stability. These theoretical studies are crucial for identifying feasible pathways toward real-world applications. Efforts are also being made to better understand the properties of exotic matter. Researchers are investigating potential sources of negative energy density, such as the Casimir effect, which could provide insights into the practical generation and manipulation of exotic matter. Quantum field theory plays a significant role in this research. By studying the behavior of quantum fields in curved spacetime, physicists aim to uncover mechanisms that could produce the necessary negative energy conditions for a warp drive. Experimental physics is pushing the boundaries of what is possible with current technology. High-energy particle accelerators and advanced detectors are used to probe the fundamental properties of matter and energy, seeking phenomena that could be harnessed for advanced propulsion systems. Researchers are also exploring alternative propulsion methods that might serve as stepping stones toward warp drive technology. Ion drives, plasma propulsion, and other advanced concepts are being developed to increase the efficiency and speed of space travel. NASA's EagleWorks laboratory is one of the notable institutions involved in this cutting-edge research. Although their work on the warp drive and related concepts is still in the preliminary stages, it has generated significant interest and laid the groundwork for future studies. Collaborations between theoretical physicists and engineers are essential for translating abstract concepts into practical technologies. These interdisciplinary efforts aim to address the myriad challenges involved in developing a functional warp drive. International cooperation is also vital. Agencies like the European Space Agency, ESA, and private space companies are contributing to the broader effort by funding research and fostering innovation in space propulsion technologies. Public interest in faster-than-light travel helps drive funding and support for these research initiatives. Popular science fiction and media coverage raise awareness and inspire the next generation of scientists and engineers to pursue careers in space exploration and advanced physics. Educational institutions are playing a crucial role by integrating advanced physics and engineering courses into their curricula. These programs train students in the necessary skills and knowledge to contribute to the future of faster-than-light travel research. Gravitational wave observatories, such as LIGO and Virgo, provide valuable data that can inform theoretical models. By studying the ripples in spacetime caused by massive cosmic events, scientists gain insights into the fundamental nature of spacetime itself. Computational advancements are enabling more sophisticated simulations of warp drive scenarios. High-performance computing allows researchers to model complex interactions and test various configurations under different conditions, providing deeper insights into the feasibility of warp drives. Ethical and philosophical discussions are also part of the ongoing research. Considering the potential implications of faster-than-light travel for humanity and the broader universe helps guide responsible development and application of these technologies. While practical warp drive technology may still be far off, the progress made in theoretical research, experimental physics, and interdisciplinary collaboration keeps the dream alive. Each discovery and innovation brings us a step closer to understanding the possibilities and limitations of faster-than-light travel. Criticisms and theoretical issues surrounding the concept of faster-than-light travel are numerous and complex. One major criticism is the requirement for exotic matter with negative energy density. The existence of such matter is purely theoretical, and no experimental evidence has confirmed its presence or practical utility. Another significant issue is the immense energy requirements for creating and sustaining a warp bubble. Even with optimistic projections, the energy needed far exceeds what current or foreseeable technology can produce, making the concept impractical with our current understanding. The stability of the warp bubble poses another theoretical challenge. Small perturbations could potentially collapse the bubble, making sustained faster-than-light travel difficult if not impossible. Ensuring stability would require precise control over the warp field, which is beyond our current capabilities. The interaction of the warp bubble with the surrounding environment is also problematic. As the bubble moves, it could accumulate high-energy particles and radiation, which could be released explosively when the bubble is turned off, posing a significant hazard. Causality violations present another major issue. Faster-than-light travel could theoretically lead to scenarios where cause and effect are reversed, creating paradoxes that challenge the very foundations of our understanding of time and physics. Some physicists argue that even if a warp drive could be theoretically possible, the practical engineering challenges are insurmountable. The need for materials that can withstand extreme conditions, precise control mechanisms, and vast amounts of energy all present formidable obstacles. Critics also point out that alternative methods of space exploration, such as generation ships or cryogenic sleep, might be more feasible than attempting to achieve faster-than-light travel. These methods, while slower, are based on technology that is more within our reach. The impact on the fabric of spacetime itself is another concern. Manipulating spacetime on such a scale could have unforeseen consequences, potentially destabilizing local or even larger-scale cosmic structures. Ethical considerations also arise when contemplating faster-than-light travel. The potential for exploitation, unintended consequences, and the impact on human society and other possible civilizations must be carefully considered. Theoretical physicists continue to debate whether the principles underlying warp drives are consistent with the known laws of physics. Some argue that solutions to the equations of general relativity that allow for warp drives are merely mathematical curiosities without physical relevance. The concept of a warp drive also hinges on assumptions about the nature of space-time and energy that may not hold true in all conditions. Further advances in our understanding of quantum gravity and the unification of general relativity with quantum mechanics are needed to address these assumptions. Experimental tests to detect phenomena that might support the existence of exotic matter or negative energy are challenging and have so far yielded no definitive results. This lack of empirical evidence casts doubt on the feasibility of warp drives. Interdisciplinary collaboration is necessary to address the myriad challenges of faster-than-light travel. Combining insights from physics, engineering, cosmology, and even philosophy is crucial for developing a comprehensive understanding and potential solutions. Despite these criticisms and challenges, the pursuit of faster-than-light travel remains a valuable scientific endeavor. It pushes the boundaries of our knowledge and inspires innovation across multiple fields, even if practical warp drives remain elusive. Theoretical issues and criticisms highlight the complexity of the challenge, but they also guide research by identifying the key obstacles that must be overcome. The ongoing debate and investigation into faster-than-light travel continue to enrich our understanding of the universe. Quantum mechanics is a fundamental theory in physics that describes the behavior of particles at the smallest scales. It emerged in the early 20th century to explain phenomena that classical physics could not, such as the behavior of electrons in atoms. One of the key principles of quantum mechanics is wave-particle duality. Particles like electrons and photons exhibit both wave-like and particle-like properties, depending on how they are observed. This duality is central to understanding the behavior of quantum systems. Another core concept is the uncertainty principle, formulated by Werner Heisenberg. It states that certain pairs of properties, such as position and momentum, cannot both be precisely measured simultaneously. The more accurately one property is known, the less accurately the other can be known. Quantum mechanics also introduces the idea of quantization. Energy levels in atoms are quantized, meaning electrons can only exist in specific energy states. This explains the discrete spectral lines observed in atomic emissions. Superposition is another fundamental principle. It means that particles can exist in multiple states at once until they are measured. This leads to phenomena such as interference patterns observed in the famous double-slit experiment. Entanglement is a unique and non-intuitive aspect of quantum mechanics. When particles become entangled, the state of one particle is instantly correlated with the state of another, no matter the distance between them. This connection appears to violate classical notions of locality. Quantum tunneling is a phenomenon where particles can pass through potential barriers that would be insurmountable according to classical physics. This effect is crucial for understanding processes like nuclear fusion in stars and the operation of certain types of semiconductor devices. The Schrödinger equation is a key mathematical tool in quantum mechanics. It describes how the quantum state of a physical system changes over time. Solutions to the Schrödinger equation provide the probabilities of finding particles in various states. Quantum mechanics also has profound implications for information theory. The field of quantum computing leverages principles like superposition and entanglement to perform calculations that would be infeasible for classical computers. The Copenhagen interpretation, one of the earliest and most widely taught interpretations of quantum mechanics, posits that a particle's wave function collapses to a single state upon measurement. However, other interpretations, such as the many worlds interpretation, suggest that all possible outcomes actually occur in parallel universes. Quantum mechanics has been extremely successful in explaining and predicting a wide range of phenomena. Technologies such as lasers, MRI machines, and transistors are direct applications of quantum principles. Despite its successes, quantum mechanics remains an area of active research and debate. Questions about the nature of reality, the role of the observer, and the integration of quantum mechanics with general relativity continue to challenge physicists. Quantum field theory extends quantum mechanics to fields, such as the electromagnetic field, and forms the basis for the standard model of particle physics. This model successfully describes three of the four known fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Experimental tests of quantum mechanics, such as Bell's theorem and various quantum optics experiments, consistently confirm the theory's predictions. These experiments continue to push the boundaries of our understanding and reveal new quantum phenomena. Quantum mechanics revolutionized our view of the physical world. It challenges our intuitions and provides a framework for understanding the fundamental nature of reality at the smallest scales, continuing to inspire and drive advancements in science and technology. Quantum entanglement is one of the most intriguing and perplexing phenomena in quantum mechanics. When two particles become entangled, their states are interconnected in such a way that the state of one particle instantaneously affects the state of the other, no matter the distance between them. This phenomenon was famously described by Albert Einstein as spooky action at a distance. Einstein, along with Boris Podolsky and Nathan Rosen, formulated the EPR paradox in 1935 to highlight what they saw as the incompleteness of quantum mechanics. Entanglement occurs when particles interact in ways that cause their quantum states to become correlated. Once entangled, the properties of the particles, such as their spin, polarization, or momentum, become linked. Measuring one entangled particle determines the state of the other. If two particles are entangled and one is measured to have a certain spin, the other particle's spin will instantly align accordingly, even if they are light years apart. This instantaneous connection seems to violate the principle of locality, which states that an object is directly influenced only by its immediate surroundings. However, entanglement does not allow for faster-than-light communication, as the measurement outcomes are still random. Experiments have repeatedly confirmed the reality of entanglement. Bell's theorem, proposed by physicist John Bell in 1964, provided a way to test the predictions of quantum mechanics against those of local realism. Experimental results consistently support the predictions of quantum mechanics. Quantum entanglement has practical applications in emerging technologies. Quantum computing leverages entanglement to perform complex computations more efficiently than classical computers. Entangled qubits, the basic units of quantum information, can represent and process information in ways that classical bits cannot. Quantum cryptography uses entanglement to create secure communication channels. The principle of quantum key distribution, such as in the BB84 protocol, ensures that any attempt to eavesdrop on the communication will be detected, providing an unprecedented level of security. Entanglement also plays a role in quantum teleportation, a process by which the quantum state of a particle can be transmitted from one location to another without physically moving the particle itself. This relies on the entanglement of particles and the transfer of classical information. The study of entanglement extends into the realms of condensed matter physics and quantum field theory, where it helps to understand phenomena such as phase transitions and the entanglement entropy of systems. Entanglement is also being explored in the context of quantum networks. These networks aim to link multiple quantum devices across large distances, creating a new infrastructure for quantum communication and distributed quantum computing. One of the significant challenges in utilizing entanglement is maintaining coherence. Entangled states are delicate and can be easily disrupted by interactions with the environment, a problem known as decoherence. Researchers are developing methods to preserve and control entanglement in practical applications. The philosophical implications of entanglement are profound. It challenges our classical intuitions about separability and locality, suggesting a more interconnected and holistic view of the universe. Entanglement raises questions about the nature of reality and the role of the observer in the quantum world. Despite its counterintuitive nature, entanglement is a well-established and experimentally verified phenomenon. It continues to be a central topic of research, driving advances in both theoretical and applied physics. As we develop a deeper understanding of entanglement, we move closer to harnessing its full potential. The implications for technology, communication, and our fundamental understanding of the universe are vast and transformative. Quantum entanglement remains a fascinating frontier in science. Its study not only pushes the boundaries of quantum mechanics, but also promises to revolutionize the way we interact with and comprehend the quantum world. Quantum tunneling is a phenomenon where particles pass through energy barriers that, according to classical physics, they shouldn't be able to cross. This process is crucial for understanding various physical phenomena at the atomic and subatomic levels. In classical physics, a particle encountering a barrier with higher energy than the particle's energy would be reflected back. However, quantum mechanics allows for a probability that the particle can tunnel through the barrier, appearing on the other side. This probability is a result of the wave-like nature of particles. When a particle approaches a barrier, its wave function extends into and beyond the barrier. If the barrier is thin enough, the wave function can continue on the other side, allowing the particle to tunnel through. In electronics, tunneling is the principle behind tunnel diodes and transistors. These components exploit tunneling to achieve fast switching times and operate at low voltages, which is vital for modern electronics and computing technologies. Quantum tunneling also plays a role in radioactive decay. Certain nuclei can decay by tunneling through the potential energy barrier surrounding them, a process that would be forbidden by classical physics due to the insufficient energy of the particles involved. The scanning tunneling microscope, or STM, is a powerful application of quantum tunneling. It uses the tunneling current between a sharp metal tip and the surface being studied to produce atomic-scale images of materials. The STM has revolutionized surface science and nanotechnology. In chemistry, tunneling contributes to reaction rates, especially at low temperatures. Some chemical reactions proceed much faster than predicted by classical mechanics due to the tunneling of particles involved in bond formation and breaking. The mathematics of tunneling involves solving the Schrödinger equation for a particle in a potential barrier. The solution provides the probability amplitude for the particle's presence on either side of the barrier, indicating the likelihood of tunneling occurring. Quantum tunneling demonstrates the non-intuitive nature of quantum mechanics. It reveals that particles do not follow deterministic paths but instead have probabilistic behaviors, which can lead to seemingly impossible outcomes like tunneling. The phenomenon also has implications for the stability of matter. Tunneling limits the longevity of certain states, contributing to phenomena such as the eventual decay of protons, although this process occurs over extraordinarily long timescales. Researchers continue to explore the implications and applications of tunneling. In quantum computing, for example, tunneling could potentially enable new types of qubits and gate operations, enhancing computational power and efficiency. In cosmology, quantum tunneling is proposed as a mechanism for events like the early inflation of the universe. Tunneling between different vacuum states could explain rapid expansion phases and the formation of the universe's large-scale structure. Understanding tunneling deepens our comprehension of quantum mechanics and the fundamental nature of particles. It challenges our classical intuitions and highlights the rich, probabilistic landscape of the quantum world. Quantum tunneling is a cornerstone concept in modern physics. Its effects are pervasive across various fields, from the tiniest particles to the vast cosmos, illustrating the profound impact of quantum mechanics on our understanding of the universe. Potential applications for faster-than-light travel, if it becomes possible, are vast and transformative. One of the most obvious applications is interstellar exploration. FTL travel would allow us to reach distant stars and exoplanets within human lifetimes, making manned missions to other solar systems feasible. Colonization of other planets becomes a practical reality with FTL travel. Entire new worlds could be settled, expanding the human presence throughout the galaxy. This could help ensure the survival of humanity by providing alternative habitats in case of catastrophic events on Earth. Resource acquisition from other star systems is another significant application. Planets and asteroids in other systems might possess resources that are rare or depleted on Earth. FTL travel would make it possible to mine these resources and transport them back to our solar system. FTL travel would revolutionize communication. Currently, messages sent to even the nearest stars would take years to arrive. With FTL capabilities, instant or near instantaneous communication across vast distances becomes possible, facilitating coordination and collaboration on a galactic scale. Scientific research and exploration would benefit immensely. Astronomers and physicists could directly study phenomena such as black holes, neutron stars, and other cosmic objects up close, gaining insights that are impossible to obtain from Earth. Trade and commerce would expand beyond our solar system. Goods and services could be exchanged with other civilizations, assuming we find or establish contact with intelligent extraterrestrial life. This could lead to a new era of economic growth and cultural exchange. Military and defense strategies would also be transformed. FTL travel could provide strategic advantages by enabling rapid deployment of assets and quick responses to threats. It would also necessitate new forms of defense against potential FTL-capable adversaries. Humanitarian missions could reach disaster-struck regions on other planets quickly, whether providing aid to a colony experiencing a natural disaster or relocating populations from endangered areas. FTL travel would make such missions timely and effective. Tourism would take on a whole new dimension. Sightseeing trips to other star systems, visits to exotic alien worlds, and experiencing different planetary environments firsthand would become possible, creating a whole new industry. Cultural exchange with extraterrestrial civilizations could lead to unprecedented advancements in knowledge and technology. If other intelligent species exist and can be contacted, the exchange of ideas and technologies could accelerate human progress in ways we cannot currently imagine. Environmental management could extend beyond Earth. For example, waste disposal might involve sending hazardous materials to uninhabited regions of space, or terraforming efforts could transform lifeless planets into habitable environments. FTL travel could also enable new forms of scientific experiments that require conditions not present in our solar system. This includes studying the effects of different gravitational environments, unique planetary atmospheres, and unknown cosmic phenomena. Medical advancements might benefit from access to extraterrestrial biomes. Discovering new forms of life with unique biological properties could lead to breakthroughs in medicine, potentially curing diseases and extending human lifespans. Art and culture would be enriched by the experiences and inspirations drawn from exploring the galaxy. The influence of other worlds and potential alien civilizations could lead to new artistic movements and cultural renaissances. Finally, FTL travel would fundamentally change our perspective on life and our place in the universe. The ability to traverse the stars would redefine our understanding of distance, time, and existence, fostering a new era of exploration and discovery that could unite humanity in the pursuit of a common destiny among the stars. Despite the exciting possibilities of faster-than-light travel, significant limitations and challenges remain. Theoretical models, such as the Alcubierre drive, rely on exotic matter with negative energy density, which has not been discovered or created in practical amounts. Energy requirements for creating and maintaining a warp bubble are immense. Current estimates suggest the need for energy on a scale far beyond what our most advanced technologies can produce, presenting a major hurdle for practical implementation. Stability of the warp bubble is another critical issue. Small perturbations could destabilize the bubble, causing it to collapse and potentially endanger the spacecraft and its occupants. Ensuring long-term stability requires precise control mechanisms that are not yet available. Interaction with the surrounding environment poses additional risks. As the warp bubble moves, it could accumulate high-energy particles and radiation, which might be released explosively when the bubble is turned off, creating significant hazards. Navigating through space with a warp drive presents unique challenges. Traditional navigation methods based on celestial landmarks might not apply, requiring the development of new techniques to guide a spacecraft traveling faster than light. The impact on the fabric of spacetime itself is a concern. Manipulating spacetime on such a scale could have unforeseen consequences, potentially destabilizing local or even larger-scale cosmic structures. Communication with a spacecraft using a warp drive would be difficult. Signals traveling at the speed of light would lag behind a faster-than-light spacecraft, complicating real-time communication and coordination with mission control. Ethical considerations also arise. The potential for misuse of faster-than-light travel, unintended consequences, and the impact on human society and other possible civilizations must be carefully considered and addressed. Research into quantum field theory and general relativity continues to explore the fundamental principles underlying faster-than-light travel. These studies aim to identify possible mechanisms and conditions under which such travel could occur. Experimental tests to detect phenomena that might support the existence of exotic matter or negative energy are ongoing. However, these tests face significant technical challenges and have yet to yield definitive results. Interdisciplinary collaboration is essential. Physicists, engineers, cosmologists, and even philosophers must work together to address the myriad challenges of faster-than-light travel and develop comprehensive solutions. Advancements in related fields such as quantum computing and material science may provide breakthroughs that could eventually contribute to faster-than-light travel. These advancements might help solve some of the energy and stability issues currently faced. Public interest and funding play a crucial role in supporting research efforts. Increased awareness and investment in space exploration and advanced physics can drive progress and bring us closer to overcoming the limitations of faster-than-light travel. Educational institutions are crucial for training the next generation of scientists and engineers. Incorporating advanced physics and engineering courses into curricula ensures that students gain the necessary skills and knowledge to contribute to future breakthroughs. As research progresses, each discovery brings us a step closer to understanding the possibilities and limitations of faster-than-light travel. While significant challenges remain, the pursuit of this ambitious goal continues to inspire and drive innovation across multiple fields. Tachyons are hypothetical particles that move faster than light. The concept was first introduced in 1967 by physicists Gerald Feinberg and George Sudarshan. According to special relativity, tachyons would have imaginary mass, leading to speeds greater than the speed of light. Tachyons derive their name from the Greek word tachys, meaning swift. These particles have never been observed, but their theoretical existence stems from the equations of relativity, which suggest the possibility of particles with imaginary mass. Unlike ordinary particles that slow down as they lose energy, tachyons would behave oppositely. As they lose energy, their speed increases. Conversely, gaining energy would cause them to slow down, approaching the speed of light from above. One intriguing aspect of tachyons is their potential to reverse the conventional relationship between cause and effect. If they exist, tachyons could transmit information back in time, challenging our understanding of causality and temporal order. Mathematically, tachyons arise from solutions to the relativistic energy-momentum relation. When solving for a particle with imaginary mass, the equations predict speeds exceeding the speed of light. These solutions are consistent with special relativity, but require a new interpretation of mass and energy. The concept of tachyons has been explored in various theoretical frameworks, including string theory. In some models, tachyonic fields represent instabilities that can lead to spontaneous symmetry breaking, a process important in the early universe. Despite their theoretical basis, tachyons face significant skepticism within the scientific community. No experimental evidence supports their existence, and many physicists consider them more of a mathematical curiosity than a real physical entity. Tachyons have found a place in popular culture and science fiction. They are often depicted as means for faster-than-light communication or time travel, capturing the imagination of writers and audiences alike. In particle physics, the search for tachyons involves looking for deviations, from expected behaviors of particles at high energies. So far, experiments using particle accelerators and cosmic ray detectors have found no evidence of tachyons. If tachyons were discovered, it would revolutionize our understanding of physics. Their existence would require rethinking fundamental principles, including the nature of mass, energy, and the structure of spacetime. Theoretical models sometimes use tachyons to explore boundaries of existing theories. By examining how tachyons would interact with known particles and fields, physicists can test the robustness and limits of current frameworks, like the Standard Model. Tachyon fields in string theory represent directions in which the system can lower its energy. The condensation of tachyons can lead to the stabilization of the system, providing insights into the dynamics of the early universe and phase transitions. Some speculative theories suggest that tachyons could be related to dark energy or other unknown cosmic phenomena. If true, they might help explain the accelerated expansion of the universe or other large-scale structures. Despite the lack of experimental evidence, tachyons continue to be a useful theoretical tool. They challenge physicists to think beyond conventional limits and explore new possibilities for understanding the universe. The ongoing study of tachyons highlights the dynamic and ever-evolving nature of theoretical physics. As our knowledge expands, concepts like tachyons remind us of the potential for discovering new and unexpected aspects of reality. Tachyons possess intriguing properties that distinguish them from ordinary particles. Their most notable characteristic is their ability to travel faster than the speed of light. This superluminal speed arises from their theoretical imaginary mass, which fundamentally alters their behavior compared to particles with real mass. As tachyons lose energy, their speed increases. This counterintuitive behavior contrasts sharply with everyday experiences and classical physics, where particles slow down as they lose energy. For tachyons, gaining energy causes them to slow down, approaching the speed of light from above. The relationship between energy, momentum, and velocity for tachyons is described by modified versions of the relativistic equations. These equations suggest that tachyons would have real momentum and energy, despite having imaginary mass. In terms of interactions, tachyons would be expected to behave differently from particles with real mass. They might interact with other particles in unique ways, potentially leading to observable effects that could help identify their presence. Tachyons could theoretically transmit information faster than light. This property raises the possibility of faster-than-light communication, which would revolutionize how we understand information transfer across vast distances. However, the superluminal speeds of tachyons also introduce challenges to our understanding of causality. If tachyons could travel back in time, they might create paradoxes where cause and effect are reversed, complicating the fundamental laws of physics. In quantum field theory, tachyonic fields represent unstable states that can lead to spontaneous symmetry breaking. This process is important in explaining phenomena such as the Higgs mechanism, which gives particles their mass through interactions with the Higgs field. The instability associated with tachyonic fields suggests that if tachyons exist, they might not be stable particles. Instead, they could represent transitional states that decay into other particles or fields, contributing to various physical processes. Some theories propose that tachyons might be connected to dark energy, the mysterious force driving the accelerated expansion of the universe. If tachyons contribute to dark energy, they could help explain the dynamics of cosmic inflation and the structure of space-time. In the context of string theory, tachyons can appear as modes of vibration that indicate instabilities in the string landscape. The condensation of these tachyonic modes can lead to more stable configurations, providing insights into the early universe's evolution and the formation of matter. Experimental searches for tachyons involve looking for deviations from expected particle behavior at high energies. So far, no definitive evidence of tachyons has been found, but ongoing research continues to push the boundaries of particle physics. Tachyons also challenge the conventional understanding of the speed limit set by the speed of light. If they exist, they would require a re-evaluation of the principles underlying special relativity and potentially lead to a more comprehensive theory of physics. Despite their speculative nature, tachyons serve as valuable theoretical tools. They help physicists explore the limits of current theories and consider new possibilities for understanding the fundamental nature of the universe. The study of tachyons highlights the importance of open-mindedness in scientific inquiry. While their existence remains unproven, the exploration of their properties and behavior encourages innovative thinking and pushes the frontiers of knowledge. As research continues, tachyons remain a captivating topic in theoretical physics. Whether they exist or not, their study contributes to a deeper understanding of the universe and the ongoing quest to uncover the mysteries of the cosmos. Tachyons, with their unique property of moving faster than light, could potentially enable faster-than-light travel if they exist and can be harnessed. By understanding and manipulating tachyons, we might develop new methods of propulsion that transcend the light-speed barrier. One way tachyons could facilitate FTL travel is through communication. If we can use tachyons to send signals faster than light, it would revolutionize space communication, allowing for instant data transfer across vast interstellar distances. Tachyon-based propulsion systems might work by creating a field or bubble around a spacecraft that allows it to move at superluminal speeds. This concept, while highly speculative, could theoretically bypass the limitations imposed by conventional physics. Another potential application is in the realm of warp drives. Tachyons could be involved in generating the exotic matter needed to stabilize a warp bubble, enabling a spacecraft to travel faster than light without violating the known laws of physics. Tachyons could also play a role in creating and stabilizing wormholes. If they can be used to manipulate spacetime effectively, tachyons might help open stable, traversable wormholes, providing shortcuts across the cosmos. The ability of tachyons to transmit information instantaneously might lead to new forms of navigation and control systems for FTL spacecraft. These systems could respond in real time, even over vast distances, ensuring precise and safe travel. In theoretical physics, tachyons challenge our understanding of causality and the structure of spacetime. By studying these particles, we might uncover new principles that could be applied to develop FTL technologies. Harnessing tachyons for FTL travel would likely require breakthroughs in our understanding of quantum mechanics and general relativity. We would need to integrate these particles into a coherent framework that explains their behavior and interactions. If tachyons can interact with normal matter, they might be used to create new forms of energy or propulsion systems. This interaction could potentially reduce the energy requirements for FTL travel, making it more feasible with existing or near-future technology. Experimental detection of tachyons would be a significant first step. By confirming their existence and properties, scientists could begin to explore practical applications, moving from theoretical speculation to real-world engineering. The potential of tachyons extends to the concept of time travel. If tachyons can move backward in time, they might allow for communication with the past or future, opening up new possibilities for manipulating time itself. Understanding how to stabilize and control tachyons would be crucial. Any practical application for FTL travel would need to ensure that these particles can be reliably generated, directed, and contained without causing harmful side effects. Theoretical models involving tachyons could also provide insights into higher dimensions or alternate realities. If these particles can move through different dimensions, they might offer new routes for FTL travel that bypass conventional spacetime. Tachyons might also contribute to new technologies for energy storage and generation. By exploiting their unique properties, we could develop more efficient systems that support the high energy demands of FTL travel. The exploration of tachyons represents the frontier of theoretical physics. While practical applications remain speculative, the study of these particles continues to inspire innovative thinking and the pursuit of knowledge beyond the limits of current scientific understanding. Experimental searches for tachyons have been ongoing for decades, although no definitive evidence has been found. Researchers use various methods to detect these hypothetical particles, focusing on their unique properties and potential interactions with known particles. Particle accelerators are one of the primary tools used in the search for tachyons. High-energy collisions in these accelerators can produce a wide range of particles, and scientists analyze the resulting data for any anomalies that might indicate the presence of tachyons. One approach involves looking for deviations from expected behavior in particle decay processes. Tachyons would introduce changes in the decay patterns of certain particles, providing indirect evidence of their existence. Cosmic ray experiments also play a role in the search for tachyons. Cosmic rays are high-energy particles that originate from outer space and strike the Earth's atmosphere. By studying these interactions, researchers hope to detect signs of tachyons or their effects. Detectors designed to identify faster-than-light particles have been developed and deployed in various experiments. These detectors measure the speed and energy of particles, looking for those that exceed the speed of light, a potential signature of tachyons. One notable experiment is the OPERA project, which initially reported faster-than-light neutrinos. However, further investigation revealed that this result was due to a measurement error, underscoring the challenges and complexities involved in searching for tachyons. Another significant experiment is the Tachyon Search Experiment at Fermilab. This project aims to detect tachyons by looking for time anomalies in particle interactions, which would indicate the presence of particles traveling backward in time. Despite the lack of direct evidence, some researchers have proposed that tachyons could be detected through their gravitational effects. If tachyons contribute to dark energy or other cosmic phenomena, their influence might be observable in the large-scale structure of the universe. Advanced theoretical models continue to guide experimental searches. These models predict specific conditions and interactions where tachyons might be detectable, helping to refine experimental setups and analysis techniques. Quantum field theory provides another avenue for exploring tachyons. By studying the behavior of quantum fields under extreme conditions, scientists can identify potential signatures of tachyons and design experiments to test these predictions. The Large Hadron Collider, LHC, at CERN, is one of the most powerful tools for investigating tachyons. Its high-energy collisions provide a fertile ground for discovering new particles, including hypothetical ones like tachyons. Astrophysical observations also contribute to the search. By studying high-energy cosmic events and the behavior of particles in extreme environments, researchers hope to find indirect evidence of tachyons or their effects. Collaboration between experimental and theoretical physicists is crucial. Theoretical insights guide the design of experiments and the interpretation of data, while experimental findings provide feedback for refining theoretical models. The search for tachyons is part of a broader effort to understand the fundamental nature of the universe. While finding these particles would be groundbreaking, the research process itself advances our knowledge and spurs technological innovation. As technology and methodologies improve, the search for tachyons continues. Each experiment brings us closer to answering one of the most intriguing questions in modern physics: whether these faster-than-light particles exist and how they might transform our understanding of the cosmos. Dark energy and dark matter are two of the most mysterious components of the universe. Together, they make up about 95% of the total mass-energy content of the cosmos, yet they remain largely undetected and poorly understood. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible to current telescopes. Its presence is inferred from its gravitational effects on visible matter, such as stars and galaxies. One of the key pieces of evidence for dark matter comes from observing the rotation curves of galaxies. Stars at the edges of galaxies rotate faster than can be accounted for by the visible mass alone, suggesting the presence of an unseen mass. Dark matter also plays a crucial role in the formation and evolution of large-scale structures in the universe. It acts as a gravitational scaffold around which galaxies and galaxy clusters form and grow. There are several candidates for dark matter particles, including WIMPs, or weakly interacting massive particles, and axions. These particles are hypothesized to interact only through gravity and the weak nuclear force, making them extremely difficult to detect. Dark energy, on the other hand, is a mysterious force that is driving the accelerated expansion of the universe. Its discovery in the late 1990s was one of the most significant developments in cosmology. The existence of dark energy was first suggested by observations of distant supernovae, which appeared dimmer than expected, indicating that the universe's expansion is speeding up rather than slowing down. Dark energy is thought to make up about 68% of the universe's total energy content. Its exact nature is unknown, but it is often modeled as a cosmological constant, a uniform energy density that fills space homogeneously. Alternative theories propose that dark energy could be a dynamic field, similar to the Higgs field, that varies over time and space. This concept is known as quintessence. The nature of dark energy has profound implications for the ultimate fate of the universe. If it remains constant, the universe will continue to expand forever. If it changes over time, it could lead to scenarios such as the Big Rip, where the expansion becomes so rapid that all matter is torn apart. The study of dark energy and dark matter involves a variety of observational techniques. These include galaxy surveys, cosmic microwave background measurements, and gravitational lensing, which can reveal the distribution of dark matter. Experiments such as the Large Underground Xenon, LUX detector, and the Alpha Magnetic Spectrometer, AMS, on the International Space Station are designed to directly detect dark matter particles. So far, no definitive detections have been made. Theoretical physicists are also working to integrate dark matter and dark energy into the standard model of particle physics. This effort requires new physics beyond the current framework, as neither dark matter nor dark energy fits neatly into the existing model. Understanding dark matter and dark energy is one of the biggest challenges in modern physics. These components hold the key to understanding the universe's structure, evolution, and ultimate fate. As research continues, new technologies and observations may provide the breakthroughs needed to unravel these cosmic mysteries. The pursuit of this knowledge drives innovation and inspires a deeper exploration of the universe. The study of dark energy and dark matter exemplifies the vast unknowns that still exist in our understanding of the cosmos. It challenges scientists to push the boundaries of current theories and explore new realms of physics, promising exciting discoveries in the years to come. Dark energy and dark matter have profound influences on the universe's expansion. Dark energy, in particular, is the driving force behind the accelerated expansion of the universe, a phenomenon first discovered in the late 1990s. The discovery was made by observing distant Type Ia supernovae, which appeared dimmer than expected. This indicated that the universe's expansion rate was not slowing down due to gravity, as previously thought, but was instead speeding up. Dark energy is often modeled as a cosmological constant, a term originally introduced by Albert Einstein in his equations of general relativity. This constant represents a uniform energy density that permeates all of space and exerts a repulsive force, counteracting the effects of gravity. As the universe expands, the influence of dark energy becomes more dominant. In the early universe, matter and radiation were the primary forces driving expansion. However, as the universe has grown larger and less dense, dark energy now plays the leading role. Dark energy's repulsive force affects not only the rate of expansion, but also the geometry of the universe. Current observations suggest that the universe is flat, meaning that the amount of dark energy perfectly balances the gravitational pull of matter. Dark matter, while not directly influencing the expansion rate, plays a crucial role in the structure and evolution of the universe. Its gravitational effects are essential for the formation of galaxies and galaxy clusters. Without dark matter, the gravitational pull of visible matter alone would be insufficient to form the structures we observe today. Dark matter acts as a scaffold, providing the necessary gravitational pull to bind galaxies and clusters together. The interplay between dark matter and dark energy shapes the large-scale structure of the universe. Dark matter clumps together under the influence of gravity, forming the cosmic web of filaments and voids that define the universe's structure. As the universe expands, dark energy works against the gravitational pull of dark matter, influencing the rate at which galaxies and clusters move apart. This delicate balance affects the distribution and evolution of cosmic structures over time. Observations of the cosmic microwave background, the afterglow of the Big Bang, provide crucial evidence for the influence of dark matter and dark energy. The patterns of temperature fluctuations in this background radiation reveal information about the early universe's composition and expansion history. Galaxy surveys and gravitational lensing studies also contribute to our understanding of dark matter and dark energy. By mapping the distribution of galaxies and the bending of light by massive objects, scientists can infer the presence and influence of dark matter and dark energy.
Future missions, such as the Euclid satellite and the James Webb Space Telescope, aim to provide even more detailed observations of the universe's expansion and structure. These missions will help refine our understanding of dark energy's role and the nature of dark matter.
The influence of dark energy on the universe's expansion also has implications for its ultimate fate. If dark energy remains constant, the universe will continue to expand forever, leading to a cold, dark, and empty cosmos. Alternatively, if dark energy increases over time, it could result in a scenario known as the Big Rip, where the expansion becomes so rapid that galaxies, stars, planets, and even atomic structures are torn apart. Understanding the influence of dark energy and dark matter on the universe's expansion is one of the central goals of modern cosmology. It challenges our understanding of fundamental physics and drives the search for new theories that can explain these mysterious components. As we continue to explore these influences, we gain deeper insights into the nature of the universe and its underlying forces. The study of dark energy and dark matter not only expands our knowledge, but also inspires new questions about the cosmos and our place within it. Theoretical discussions about faster-than-light travel often intersect with our understanding of dark energy and dark matter. These mysterious components of the universe might hold the key to unlocking faster-than-light capabilities. Dark energy, with its repulsive force driving the accelerated expansion of the universe, could be harnessed in theoretical propulsion systems. By manipulating dark energy, it might be possible to create a warp bubble that allows for faster-than-light travel. The concept of a warp drive, as proposed by Miguel Alcubierre, requires exotic matter with negative energy density. Dark energy, or a related phenomenon, could potentially provide the necessary conditions for creating and stabilizing such a bubble. Dark matter, while not directly linked to faster-than-light travel, could play a supportive role. Its gravitational effects and interactions might be harnessed to aid in the stabilization and control of warp bubbles or other FTL mechanisms. The study of dark matter and dark energy also informs our understanding of spacetime. By learning more about these components, we might discover new ways to manipulate spacetime, which is essential for any form of faster-than-light travel. Quantum theories involving dark matter and dark energy suggest that these components could interact with known particles in unique ways. If we can understand and control these interactions, it might lead to breakthroughs in propulsion technology. Theoretical models propose that dark energy could be linked to higher dimensions or parallel universes. If this is the case, faster-than-light travel might involve moving through these dimensions, bypassing the speed limit set by our three-dimensional spacetime. Experiments with dark matter and dark energy could reveal new physics beyond the standard model. These discoveries might provide the theoretical foundation needed to develop faster-than-light travel technologies. Understanding the distribution of dark matter in the universe helps us map the gravitational landscape. This knowledge could be crucial for navigating faster-than-light spacecraft, ensuring they avoid regions of intense gravitational pull that could disrupt their travel. The influence of dark energy on the universe's expansion suggests that spacetime itself is dynamic and malleable. By harnessing this property, we might develop technologies that allow for the controlled manipulation of spacetime, enabling faster-than-light travel. Theoretical physicists are exploring the possibility that dark energy is related to a field permeating all of spacetime. If we can interact with or alter this field, it might provide the means to achieve faster-than-light speeds. Dark matter's role in the formation of cosmic structures suggests it has properties we do not fully understand. Unlocking these properties could reveal new ways to generate and control the forces needed for faster-than-light travel. Some theories propose that dark energy and dark matter are manifestations of unknown particles or fields. Discovering and understanding these particles could lead to the development of new propulsion methods that transcend current technological limitations. The integration of dark matter and dark energy into existing physical theories is a work in progress. As our understanding evolves, it could pave the way for new insights into faster-than-light travel. While the practical application of dark energy and dark matter to faster-than-light travel remains speculative, their study is essential. These components of the universe challenge our understanding of physics and push us to explore the boundaries of what might be possible. As we continue to unravel the mysteries of dark energy and dark matter, we move closer to understanding the fundamental nature of the universe. This knowledge could one day make faster-than-light travel a reality, transforming our approach to space exploration and our place in the cosmos. Current research in cosmology focuses on understanding the fundamental components and large-scale structure of the universe. One major area of study is the cosmic microwave background radiation, the afterglow of the Big Bang, which provides a snapshot of the early universe. Researchers use data from satellites like the Planck Observatory to analyze temperature fluctuations in the cosmic microwave background. These fluctuations offer insights into the density, composition, and expansion rate of the universe. Another significant area of research is the study of dark energy. Scientists are working to understand its properties and how it drives the accelerated expansion of the universe. This involves observations of distant supernovae and galaxy clusters. Dark matter remains a major focus. Experiments such as the Large Underground Xenon Detector and the Alpha Magnetic Spectrometer aim to directly detect dark matter particles. Meanwhile, astronomical observations continue to map the distribution of dark matter in the universe. Gravitational waves have opened a new window into the universe. Detectors like LIGO and Virgo have observed these ripples in spacetime caused by massive cosmic events. These observations provide valuable data on black holes, neutron stars, and the fabric of spacetime itself. The study of black holes is also advancing. The Event Horizon Telescope captured the first image of a black hole's event horizon, offering direct evidence of these enigmatic objects. Ongoing research seeks to understand their formation, growth, and impact on their surroundings. Galaxy formation and evolution are crucial topics. Scientists use both observations and simulations to study how galaxies form, merge, and evolve over billions of years. This research helps explain the structure and distribution of galaxies across the cosmos. The nature of dark energy and its influence on the fate of the universe are key questions. Researchers are developing new theoretical models and conducting large-scale surveys to measure the expansion rate and understand the behavior of dark energy. Cosmologists are exploring the early universe's conditions through the study of inflation, a rapid expansion that occurred fractions of a second after the Big Bang. Understanding inflation can provide insights into the universe's initial conditions and fundamental physics. Research into the nature of time and the potential for multiple universes is also underway. Theoretical frameworks such as string theory and the multiverse hypothesis suggest that our universe might be one of many, each with its own physical laws. The study of neutrinos, elusive particles that travel through space with minimal interaction, offers another avenue for understanding the universe. Experiments like IceCube in Antarctica aim to detect high-energy neutrinos and explore their sources. Precision cosmology is becoming increasingly important. By refining measurements of fundamental constants and cosmological parameters, scientists aim to achieve a more accurate and detailed picture of the universe's history and structure. The search for exoplanets and the study of their atmospheres contribute to our understanding of planetary formation and the potential for life beyond Earth. Missions like Kepler and TESS have discovered thousands of exoplanets, many of which reside in habitable zones. Interdisciplinary collaboration is essential in cosmology. Physicists, astronomers, mathematicians, and computer scientists work together to develop models, analyze data, and simulate cosmic phenomena, driving forward our understanding of the universe. As technology and observational capabilities advance, cosmology continues to make groundbreaking discoveries. Each new finding adds to our knowledge of the universe's origins, composition, and ultimate fate, inspiring further exploration and scientific inquiry. Causality is a fundamental principle in physics, asserting that cause precedes effect. However, faster-than-light travel introduces significant challenges to this principle, potentially leading to time paradoxes. One of the most famous paradoxes is the grandfather paradox. If a person travels back in time and prevents their grandfather from meeting their grandmother, it raises the question of how the time traveler could exist in the first place. Faster-than-light travel implies that information or objects could travel back in time. This creates scenarios where events could influence their own causes, leading to contradictions and logical inconsistencies. Einstein's theory of relativity, which underpins our understanding of spacetime, suggests that superluminal travel would violate causality. This is because different observers might disagree on the sequence of events, depending on their relative motion. In the context of a warp drive, which bends spacetime to allow faster-than-light travel, the issue of causality becomes even more complex. The warping of spacetime could create closed time-like curves, paths that return to the same point in time, potentially enabling time travel. Another paradox is the bootstrap paradox, where an object or information sent back in time becomes the very source of itself in the future. This raises questions about the origin and consistency of such objects or information. Quantum mechanics introduces additional complications. While it allows for probabilistic outcomes and entanglement, it still respects causality within the framework of spacetime. Integrating quantum mechanics with faster-than-light travel remains an unresolved challenge. Some physicists propose that nature might have mechanisms to prevent causality violations, such as the Novikov self-consistency principle. This principle suggests that any action taken by a time traveler would be part of history all along, thus avoiding paradoxes. The concept of parallel universes or the multiverse offers another potential resolution. If each time travel event creates a new branching universe, the original timeline remains unaffected and paradoxes are avoided. However, this idea remains speculative. Hawking's chronology protection conjecture posits that the laws of physics prevent closed time-like curves and time travel, thus safeguarding causality. This conjecture suggests that any attempt to create a time machine would fail due to physical constraints. The potential for faster-than-light communication also raises causality concerns. If information can be sent back in time, it could be received before it was sent, leading to similar paradoxical situations. Experimental evidence to support or refute these theoretical concerns is challenging to obtain. Current technology does not allow for faster-than-light travel or communication, so these issues remain primarily theoretical. Philosophical implications of causality and time paradoxes are profound. They challenge our understanding of free will, determinism, and the nature of time itself. Resolving these issues would require a deeper understanding of the universe's fundamental structure. Advanced theories, such as string theory or quantum gravity, might offer insights into these problems. These theories aim to unify general relativity and quantum mechanics, potentially providing a framework to address causality violations and time paradoxes. Ultimately, the study of causality and time paradoxes, in the context of faster-than-light travel, continues to push the boundaries of physics and philosophy. As our understanding of the universe evolves, these concepts will remain central to our quest to understand the true nature of reality. Energy and resource constraints are significant challenges for faster-than-light travel. Creating and maintaining the conditions necessary for superluminal speeds require immense amounts of energy, far beyond current technological capabilities. One major issue is the energy requirement for generating a warp bubble, as proposed by the Alcubierre drive. Early estimates suggested that creating a bubble capable of faster-than-light travel would require an energy equivalent to the mass of Jupiter, making it impractical with existing technology. Even with more refined calculations that reduce the energy requirements, the necessary amounts remain astronomical. Achieving and sustaining these energy levels would necessitate breakthroughs in energy generation, storage, and management. Exotic matter with negative energy density is another key resource needed for faster-than-light travel. This type of matter has not been observed in nature and remains purely theoretical, posing a significant obstacle to practical implementation. Harnessing antimatter as a potential energy source is one approach being explored. Antimatter reactions release energy far more efficiently than chemical or nuclear reactions. But producing and storing antimatter in the required quantities presents substantial technical challenges. Fusion power, another promising avenue, could provide the high energy outputs needed for faster-than-light travel. However, controlled and sustained fusion reactions are still in the experimental stage, and practical fusion power remains a goal for the future. The containment and management of such high-energy systems also pose risks. Ensuring that the systems do not fail catastrophically and that they can operate safely over extended periods is essential for any practical application of faster-than-light travel. Resource constraints extend beyond energy. The materials needed to construct and maintain faster-than-light spacecraft must withstand extreme conditions, such as intense gravitational forces and high-energy radiation. Advanced materials science is required to develop these new materials. Research into nanotechnology, superconductors and other cutting-edge fields may yield the necessary breakthroughs to build robust, reliable FTL spacecraft. The development of faster-than-light travel also requires significant financial and intellectual resources. Funding large-scale research and development projects, as well as attracting and training skilled scientists and engineers, are crucial for progress. International collaboration can help address these resource constraints. By pooling resources and knowledge, countries and organizations can work together to overcome the technical and financial challenges associated with faster-than-light travel. Ethical considerations regarding the allocation of resources must also be addressed. The pursuit of faster-than-light travel must be balanced with other pressing needs, such as addressing climate change, poverty, and global health challenges. Long-term sustainability is another important factor. Ensuring that the pursuit of faster-than-light travel does not deplete resources or harm the environment is essential for responsible exploration and development. Despite these challenges, the pursuit of faster-than-light travel continues to inspire innovation and drive scientific and technological advancements. Overcoming energy and resource constraints will require creativity, collaboration, and a commitment to pushing the boundaries of what is possible. The stability of theoretical models for faster-than-light travel is a crucial aspect of their feasibility. One major concern is ensuring that these models do not lead to catastrophic instabilities that could endanger a spacecraft or its occupants. The Alcubierre drive, for instance, relies on creating a warp bubble to achieve faster-than-light speeds. However, maintaining the stability of this bubble requires precise control over spacetime distortions, which is an enormous technical challenge. Small perturbations in the warp bubble could cause it to collapse, potentially resulting in the destruction of the spacecraft. Ensuring long-term stability involves addressing how these perturbations are managed and controlled. Theoretical models must also account for the interaction between the warp bubble and the surrounding environment. As the bubble moves, it could encounter varying gravitational fields, particles, and radiation, all of which could impact its stability. Gravitational waves generated by the movement of a warp bubble might also pose risks. These waves could create feedback loops that destabilize the bubble, making it necessary to develop methods for damping or mitigating such effects. Another aspect of stability involves the energy requirements for maintaining the warp bubble. Any fluctuations in the energy supply could lead to instability, highlighting the need for a reliable and continuous energy source. Theoretical models also need to consider the cumulative effects of long-duration travel at faster-than-light speeds. Over time, even small instabilities could grow, so understanding how to manage and correct these instabilities is vital. Quantum effects might play a role in the stability of faster-than-light travel models. Quantum fluctuations could introduce unpredictable elements into the behavior of the warp bubble, necessitating a deeper understanding of quantum gravity. Material stability is another consideration. The materials used to construct a faster-than-light spacecraft must withstand the stresses and strains imposed by the warp bubble and its interactions with spacetime. Thermal stability is critical as well. The intense energy fields required for faster-than-light travel could generate significant heat, necessitating advanced cooling systems to prevent overheating and ensure the spacecraft's structural integrity. The potential for creating closed time-like curves within warp bubbles raises additional stability concerns. These curves could result in time loops and paradoxes, complicating the theoretical framework and practical implementation of faster-than-light travel. Experimental tests of theoretical models are essential for assessing their stability. Simulations and small-scale experiments can provide insights into how these models behave under different conditions, guiding further refinement and development. Peer review and collaboration within the scientific community help validate and stabilize theoretical models. By subjecting models to rigorous scrutiny and incorporating diverse perspectives, researchers can identify potential weaknesses and improve their designs. Interdisciplinary approaches are crucial for addressing stability issues. Combining insights from physics, engineering, materials science, and other fields can lead to innovative solutions that enhance the stability and feasibility of faster-than-light travel models. Ultimately, the stability of theoretical models for faster-than-light travel is a foundational aspect of their development. Ensuring that these models are robust, reliable, and safe is essential for transforming the dream of faster-than-light travel into a practical reality. Technological barriers to faster-than-light travel are numerous and daunting. Overcoming these barriers requires significant advancements in multiple areas of science and engineering. One of the primary challenges is generating the immense energy required for faster-than-light travel. Current energy generation methods, including nuclear and chemical propulsion, are far from sufficient to meet these needs.
Developing new energy sources, such as controlled nuclear fusion or antimatter reactions, is essential. These technologies could provide the high energy outputs necessary, but both remain experimental and face substantial technical hurdles.
Another barrier is the production and manipulation of exotic matter. Theoretical models often require matter with negative energy density, which has not been observed or created in practical amounts. Finding a way to produce and harness this exotic matter is critical. Maintaining the stability of a warp bubble or other faster-than-light mechanisms is another significant technological challenge. This requires precise control over space-time distortions, which involves advanced understanding and manipulation of gravitational and quantum fields. Materials capable of withstanding the extreme conditions of faster-than-light travel must be developed. These materials need to be incredibly strong and resilient to withstand intense gravitational forces, high-energy radiation, and thermal stresses. Thermal management is crucial, as the energy fields required for faster-than-light travel could generate significant heat. Advanced cooling systems and heat-resistant materials are necessary to ensure the spacecraft's structural integrity. Another technological barrier is the development of reliable and efficient energy storage systems. Storing and rapidly converting energy for use in faster-than-light propulsion requires breakthroughs in battery and capacitor technology. Navigation and control systems for faster-than-light travel present unique challenges. Traditional methods based on celestial landmarks may not apply, necessitating the creation of new technologies to guide and stabilize a spacecraft at superluminal speeds. Communication systems must also be developed to support faster-than-light travel. Signals traveling at the speed of light would lag behind, so new methods for real-time communication over vast distances are needed. The potential impact on human physiology is another concern. The extreme conditions of faster-than-light travel could affect the health and safety of astronauts, requiring advancements in medical technology and life support systems. Environmental and ethical considerations must be addressed. The pursuit of faster-than-light travel should be balanced with sustainability and responsibility, ensuring that technological advancements do not harm our planet or future generations. Collaboration across scientific disciplines is essential to overcome these technological barriers. Physicists, engineers, material scientists, and medical researchers must work together to develop comprehensive solutions. Funding and resources are also significant barriers. Large-scale research and development projects require substantial financial investment and support from governments, private enterprises, and international organizations. Public interest and education play a crucial role in driving progress. Engaging the public and fostering a culture of innovation and curiosity can help secure the necessary support and talent for advancing faster-than-light travel technologies. Despite these technological barriers, the pursuit of faster-than-light travel continues to inspire and challenge humanity. Addressing these challenges will require creativity, collaboration, and a commitment to pushing the boundaries of what is possible. Ethical considerations surrounding faster-than-light travel are complex and multifaceted. The potential consequences of such technology must be carefully weighed against its benefits. One major ethical concern is the impact on human society. The ability to travel faster than light could lead to significant social and economic disparities, as access to advanced technology might be limited to certain groups or nations. There are also concerns about the potential for military applications. Faster-than-light travel could be weaponized, leading to new forms of warfare with devastating consequences. Ensuring that this technology is used for peaceful purposes is crucial. Environmental impacts must be considered. The development and use of faster-than-light travel could have unforeseen effects on our planet's ecosystems and the broader universe. Responsible stewardship of this technology is essential to prevent harm. The exploration of new worlds raises ethical questions about the treatment of potential extraterrestrial life. If we encounter other forms of life, we must ensure that our actions do not harm or exploit them, respecting their autonomy and ecosystems. Resource allocation is another important ethical issue. Investing in faster-than-light travel should not come at the expense of addressing pressing issues on Earth, such as poverty, health, and climate change. A balanced approach is necessary. The potential for unintended consequences must be addressed. Faster-than-light travel could disrupt the fabric of spacetime, leading to unpredictable and possibly harmful effects. Rigorous testing and safeguards are needed to mitigate these risks. Privacy and surveillance concerns arise with the potential for real-time communication and travel across vast distances. Ensuring that individuals' privacy is protected and that surveillance technologies are not misused is vital. The possibility of time travel, inherent in some faster-than-light models, introduces complex ethical dilemmas. If time travel becomes feasible, the potential to alter past events raises profound questions about free will, responsibility, and the nature of history. Informed consent is critical for those participating in faster-than-light travel. Individuals must fully understand the risks and benefits involved, ensuring that their participation is voluntary and based on accurate information. The development of faster-than-light travel should involve diverse perspectives. Engaging with ethicists, sociologists, and representatives from various cultures and communities can help ensure that the technology is developed and used in a way that benefits all of humanity. Intergenerational justice is another consideration. The pursuit of faster-than-light travel should not compromise the well-being of future generations. We must ensure that our actions today do not create insurmountable problems for those who come after us. International cooperation is essential to address these ethical challenges. Establishing global norms and agreements can help ensure that faster-than-light travel is developed and used responsibly and equitably. Transparency in research and development is crucial. Open communication about the progress, risks, and potential impacts of faster-than-light travel can build public trust and foster informed decision-making. Finally, fostering a culture of ethical reflection and responsibility within the scientific and engineering communities is vital. Encouraging researchers to consider the broader implications of their work can help ensure that the pursuit of faster-than-light travel aligns with humanity's highest values and aspirations. As we continue to explore the possibilities of faster-than-light travel, addressing these ethical considerations is paramount. By doing so, we can work towards a future where this transformative technology is used wisely and responsibly, for the benefit of all. NASA's warp drive research is one of the most exciting and speculative areas of advanced propulsion studies. This research aims to explore the theoretical foundations and potential practical applications of faster-than-light travel. The concept of a warp drive, based on the Alcubierre drive theory, suggests that a spacecraft could achieve faster-than-light speeds by distorting spacetime. NASA's interest in this concept reflects a commitment to pushing the boundaries of space exploration. One of the key figures in NASA's warp drive research is Dr. Harold "Sonny" White. He has been instrumental in revisiting and refining the original Alcubierre drive concept, proposing modifications to make it more theoretically feasible. Dr. White's work focuses on reducing the energy requirements for creating a warp bubble. Initial calculations suggested an enormous energy need, but recent refinements have significantly lowered these estimates, making the concept more plausible. NASA's Eagle Works laboratory, where Dr. White conducts his research, is dedicated to exploring advanced propulsion methods. This lab is at the forefront of investigating the potential for warp drive technology and other revolutionary propulsion systems. Experiments conducted at Eagle Works involve tabletop interferometers designed to detect tiny distortions in spacetime that could indicate the presence of a warp bubble. These experiments are crucial for testing the theoretical models in a practical setting. One of the major challenges in NASA's warp drive research is the creation and manipulation of exotic matter. This type of matter, with negative energy density, is essential for maintaining a stable warp bubble, but its existence remains purely theoretical. NASA's research also explores the potential implications of warp drive technology for human space exploration. If successful, it could dramatically reduce travel times to distant stars and planets, opening up the universe for human exploration. Public interest in NASA's warp drive research has been significant. The idea of faster-than-light travel captures the imagination and inspires a sense of wonder and possibility, driving support for continued research and development. Collaboration with other institutions and international partners is a crucial aspect of NASA's approach. Sharing knowledge and resources helps to advance the research and address the numerous challenges associated with developing a practical warp drive. NASA's work on warp drive technology is part of a broader effort to develop advanced propulsion systems. This includes ion drives, nuclear thermal propulsion, and other innovative technologies that could revolutionize space travel. Theoretical studies and practical experiments at NASA are complemented by computer simulations. These simulations model the behavior of warp bubbles and other advanced propulsion concepts, providing valuable insights and guiding future research. The pursuit of warp drive technology is aligned with NASA's long-term goals for space exploration. Achieving faster-than-light travel would enable missions to explore exoplanets, investigate distant cosmic phenomena, and potentially contact extraterrestrial civilizations. While warp drive research is still in its early stages, the progress made so far is promising. Each step forward brings us closer to understanding the fundamental principles that could one day make faster-than-light travel a reality. And NASA's commitment to exploring the frontiers of propulsion technology reflects a broader vision for humanity's future in space. By pushing the limits of what is possible, NASA aims to expand our horizons and inspire the next generation of explorers and scientists. The ongoing research into warp drive technology underscores NASA's role as a leader in space exploration and innovation. As this research progresses, it continues to challenge our understanding of physics and the universe, offering the tantalizing possibility of journeys beyond our current reach. The European Space Agency, ESA, is actively involved in various initiatives aimed at advancing space exploration and technology. These initiatives are crucial for maintaining Europe's competitive edge in the global space industry. ESA's Advanced Concepts Team, ACT, explores futuristic ideas and technologies, including the theoretical foundations of faster-than-light travel. Their work includes studying exotic propulsion methods and the potential implications of breakthroughs in this field. One of ESA's flagship programs is the Ariane rocket series, which has been instrumental in launching payloads into orbit. ESA is continually upgrading this technology to increase its efficiency and payload capacity, essential for future deep space missions. ESA collaborates with international partners on missions that push the boundaries of our knowledge. The Gaia mission, for example, is mapping the Milky Way in unprecedented detail, providing valuable data for understanding the structure and dynamics of our galaxy. The Rosetta mission, which successfully landed a probe on a comet, showcased ESA's capabilities in complex space missions. The insights gained from Rosetta are helping scientists understand the early solar system and the role of comets in delivering water and organic molecules to Earth. ESA is also a key partner in the James Webb Space Telescope, JWST project. This next-generation space telescope will peer further into the universe than ever before, potentially unveiling new insights into the formation of stars, galaxies, and planetary systems. The ExoMars program, a collaboration with Roscosmos, aims to explore Mars and search for signs of past or present life. This program includes the Trace Gas Orbiter and the Rosalind Franklin rover, which will drill into the Martian surface to analyze soil samples. ESA's involvement in the International Space Station, ISS, highlights its commitment to international cooperation. European astronauts conduct scientific experiments on the ISS, contributing to our understanding of space's effects on the human body and advancing technologies for long-duration missions. The Sentinel satellites, part of the Copernicus program, monitor Earth's environment. These satellites provide critical data on climate change, natural disasters, and environmental management, underscoring ESA's commitment to addressing global challenges from space. ESA's space safety program focuses on protecting Earth from space hazards. This includes tracking space debris, monitoring near-Earth objects, NEOs, and developing technologies to mitigate potential threats, such as asteroid impacts. ESA is also pioneering the development of reusable spacecraft. The Space Rider project aims to create a reusable space transportation system that can carry payloads to and from low Earth orbit, reducing costs and increasing the frequency of missions. Quantum technology is another area of interest for ESA. The agency is exploring how quantum communication and quantum computing can enhance space missions, improve satellite security, and provide more accurate navigation systems. ESA's educational programs inspire the next generation of scientists and engineers. Initiatives like the European Space Education Resource Office, ESERO, provide resources and support for educators to teach space-related subjects, fostering interest in STEM fields among young students. Sustainable space exploration is a key priority for ESA. The agency is investigating how to use resources found on the Moon and Mars to support long-term missions, reducing the need for resupply from Earth and promoting self-sufficiency in space. ESA's commitment to innovation and international collaboration ensures that Europe remains at the forefront of space exploration. As new technologies emerge and global challenges evolve, ESA continues to play a vital role in expanding our understanding of the universe and enhancing life on Earth through space science and technology. Private sector involvement in space exploration has grown significantly in recent years, revolutionizing the industry. Companies like SpaceX, Blue Origin, and Virgin Galactic are leading the charge with innovative technologies and ambitious missions. SpaceX, founded by Elon Musk, aims to make space travel more affordable and accessible. Their development of the reusable Falcon rockets has dramatically reduced launch costs, making frequent and cost-effective missions a reality. Blue Origin, established by Jeff Bezos, focuses on sustainable space travel. Their New Shepard and New Glenn rockets are designed for reuse, with the goal of making space travel as routine as commercial air travel. Virgin Galactic, led by Richard Branson, is pioneering space tourism. Their suborbital flights offer civilians the opportunity to experience weightlessness and see the Earth from space, marking the beginning of commercial space travel for the general public. Other companies like Boeing and Lockheed Martin continue to play crucial roles in developing spacecraft and space technologies. Their partnerships with NASA and other space agencies contribute to advancements in human spaceflight and deep space exploration. Private sector investment in satellite technology is also booming. Companies like OneWeb and Starlink are deploying large constellations of small satellites to provide global internet coverage, aiming to bridge the digital divide. The involvement of private companies in space mining is another emerging field. Firms like Planetary Resources and Deep Space Industries aim to extract valuable minerals from asteroids, potentially providing resources that are rare or depleted on Earth. Private sector innovation extends to space habitats as well. Companies like Bigelow Aerospace are developing expandable modules that can be used for space stations, lunar bases, and habitats on Mars, supporting long-term human presence in space. The collaboration between private companies and government space agencies is vital. NASA's Commercial Crew Program, which partners with SpaceX and Boeing, aims to transport astronauts to the International Space Station, reducing reliance on foreign launches. Private companies are also involved in lunar exploration. NASA's Artemis program includes partnerships with commercial firms to develop lunar landers and other technologies necessary for returning humans to the Moon and establishing a sustainable presence. SpaceX's Starship program aims to enable human missions to Mars. This fully reusable spacecraft is designed to carry large numbers of people and cargo to the Red Planet, supporting Musk's vision of a self-sustaining Martian colony. Investment in space technology startups is increasing, driven by venture capital and private equity. This influx of funding supports the development of new technologies and business models, fostering a dynamic and competitive space industry. The private sector's role in space exploration is not limited to large corporations. Small and medium-sized enterprises, SMEs, are making significant contributions to innovation in areas like propulsion, materials science, and space-based services. Public-private partnerships are crucial for advancing space exploration. These collaborations leverage the strengths of both sectors, combining the innovation and efficiency of private companies with the resources and expertise of government agencies. The involvement of the private sector is transforming space exploration. As companies continue to push the boundaries of what is possible, they are driving down costs, increasing access, and opening new frontiers for humanity's journey into space. Academic research and publications play a pivotal role in advancing our understanding of faster-than-light travel and related fields. Universities and research institutions worldwide are at the forefront of theoretical and experimental studies, contributing valuable insights and breakthroughs. Peer-reviewed journals are the primary medium for disseminating new research. Publications in journals such as Physical Review Letters, Astrophysical Journal, and Journal of High Energy Physics provide a platform for scientists to share their findings and engage with the broader scientific community. Theoretical physicists explore the mathematical foundations of faster-than-light travel. Their work involves complex equations and models that attempt to describe the conditions under which superluminal speeds might be achievable, often building on the framework of general relativity and quantum mechanics. Experimental physicists conduct tests to validate or refute theoretical predictions. Their experiments, often conducted in advanced laboratories or using large-scale facilities like particle accelerators, seek to observe phenomena that could indicate the possibility of faster-than-light effects. Conferences and symposia are vital for the exchange of ideas and collaboration. Events such as the International Conference on General Relativity and Gravitation and the Symposium on Cosmology and Particle Astrophysics bring together experts to discuss the latest developments and forge new partnerships. Academic institutions also play a key role in educating the next generation of scientists. Graduate programs in physics, astronomy, and engineering provide students with the knowledge and skills needed to contribute to this cutting-edge research. Theses and dissertations often contain original research on faster-than-light travel. These documents, produced by doctoral students, add to the body of knowledge and frequently result in publications that further the field. Collaborative research projects involving multiple universities are common. These projects pool resources and expertise to tackle complex problems that no single institution could address alone, enhancing the quality and impact of the research. Grants and funding from government agencies and private foundations support academic research. Organizations such as the National Science Foundation, European Research Council, and private entities like the Simons Foundation provide crucial financial backing for innovative studies. Interdisciplinary research is increasingly important. Combining insights from physics, engineering, computer science, and other fields leads to a more comprehensive understanding of faster-than-light travel and its implications. Open access publications are making research more widely available. Journals like archive.org allow researchers to share their work freely, increasing accessibility and fostering greater collaboration and innovation across the scientific community. Review articles and meta-analyses summarize and synthesize existing research, providing valuable overviews of the current state of knowledge. These publications help identify gaps in the research and suggest directions for future studies. Workshops and seminars hosted by academic institutions offer opportunities for in-depth discussions and hands-on training. These events help researchers stay updated on the latest methodologies and technologies in the field. University-led public outreach programs educate the general public about faster-than-light travel and related topics. Lectures, exhibitions, and media appearances by academics help demystify complex concepts and inspire interest in space science. The continuous cycle of research, publication, and peer review in academia drives progress in understanding faster-than-light travel. As new discoveries are made and shared, the scientific community moves closer to unraveling the mysteries of superluminal speeds and their potential applications. Future prospects for faster-than-light travel hinge on continued advancements in theoretical physics and technological innovation. While we are still far from achieving superluminal speeds, several planned missions and research initiatives hold promise for advancing our understanding and capabilities. NASA's Artemis program aims to return humans to the Moon and establish a sustainable presence. This mission will serve as a stepping stone for deeper space exploration, providing valuable insights into the challenges of long-duration space travel. The European Space Agency's Mars Sample Return mission, in collaboration with NASA, plans to bring samples from Mars back to Earth. This mission will advance our knowledge of the Martian environment and pave the way for future human missions to Mars. The James Webb Space Telescope, set to launch soon, will explore the universe's earliest galaxies and provide critical data on cosmic phenomena. Its observations could reveal new insights into the fundamental nature of spacetime. The Breakthrough Starshot initiative aims to send small, light-powered probes to the Alpha Centauri system. Although not faster than light, these probes are designed to travel at a significant fraction of the speed of light, providing valuable data on interstellar travel. China's planned missions to explore the far side of the Moon and Mars are also significant. These missions will expand our understanding of the solar system and demonstrate new technologies for space exploration. The Lunar Gateway, an international project led by NASA, will establish a space station in lunar orbit. This platform will support missions to the Moon and beyond, testing technologies and strategies for future deep space exploration. Advances in propulsion technology are critical for future prospects. Research into ion drives, nuclear thermal propulsion, and other innovative systems continues to push the boundaries of what is possible, potentially leading to more efficient and faster space travel. Private companies like SpaceX are working on ambitious projects such as the Starship spacecraft, designed for missions to Mars and beyond. These efforts demonstrate the potential for significant breakthroughs driven by the private sector. International collaboration remains essential. Joint missions and shared research efforts help pool resources and expertise, accelerating progress towards achieving faster-than-light travel capabilities. Astrobiology missions such as Europa Clipper aim to explore the potential for life on other celestial bodies. Understanding the conditions necessary for life will inform future missions and the search for habitable exoplanets. The development of artificial intelligence and robotics will enhance our ability to explore space. Autonomous systems can perform complex tasks, gather data, and operate in environments that are challenging for human astronauts. Long-term initiatives like terraforming Mars or establishing colonies on other planets depend on advancements in many areas, including faster-than-light travel. These ambitious goals drive research and innovation across multiple disciplines. Public engagement and support are crucial for the success of future missions. Educational programs, media coverage, and outreach initiatives help build enthusiasm and investment in space exploration. Theoretical breakthroughs, such as a deeper understanding of quantum gravity or the discovery of new particles, could revolutionize our approach to faster-than-light travel. Ongoing research in fundamental physics holds the potential for paradigm-shifting discoveries. As we look to the future, the combined efforts of governments, private companies, and academic institutions will shape the trajectory of space exploration. While faster-than-light travel remains a distant goal, the advancements and missions planned today lay the groundwork for achieving what once seemed impossible. Popular science fiction has long been fascinated with the concept of faster-than-light travel. From classic literature to modern films, these portrayals have shaped our imagination and inspired real-world scientific pursuits. One of the most iconic portrayals is in the Star Trek series, where the Starship Enterprise uses warp drive to travel between star systems. This depiction has become synonymous with faster-than-light travel in popular culture. In Star Wars, spacecraft achieve faster-than-light travel using hyperdrive engines. The Millennium Falcon's ability to make the Kessel Run in less than 12 parsecs highlights the importance of speed and agility in interstellar travel. The novel Dune by Frank Herbert explores faster-than-light travel through the use of the spice melange, which allows navigators to fold space. This method combines advanced technology with mystical elements, creating a unique vision of space travel. In Isaac Asimov's Foundation series, hyperspace travel enables the vast galactic empire to function. The ability to move quickly between planets is crucial to maintaining order and communication across such a large expanse. Arthur C. Clarke's Rendezvous with Rama introduces a massive alien spacecraft traveling at high speeds, hinting at technologies far beyond human capabilities. This novel explores the awe and mystery associated with advanced space travel. The Expanse series, both in books and on television, portrays a future where humanity has colonized the solar system. While it doesn't feature faster-than-light travel, it emphasizes the challenges and complexities of space travel within our own solar system. Doctor Who features the TARDIS, a time machine and spacecraft capable of traveling anywhere in time and space. The concept of a vessel that can move freely through spacetime captures the limitless possibilities of faster-than-light travel. In the film Interstellar, a wormhole near Saturn allows for faster-than-light travel to another galaxy. This scientifically grounded portrayal emphasizes the potential of wormholes as gateways for interstellar exploration. Battlestar Galactica depicts faster-than-light travel through the use of jump drives. The ability to make instantaneous jumps across vast distances is crucial for the survival of humanity in their quest for a new home. Ender's Game by Orson Scott Card features starships capable of near-instantaneous travel, which is essential for waging interstellar war and managing a vast interplanetary empire. The story explores the strategic implications of such technology. The Hitchhiker's Guide to the Galaxy by Douglas Adams introduces the infinite improbability drive, a whimsical and humorous take on faster-than-light travel that plays with the laws of probability and physics. In Stargate, a network of ancient devices allows for instantaneous travel between distant planets. This series blends archaeology with advanced technology, exploring the implications of such a vast transportation network. The novel Hyperion by Dan Simmons features Farcasters, devices that allow for instant travel between worlds. The series delves into the social and philosophical impacts of such advanced technology. The Culture series by Iain M. Banks depicts a highly advanced society with ships capable of traveling vast distances in the blink of an eye. The series explores the ethical and cultural implications of living in a universe where distance is no longer a barrier. Science fiction's portrayals of faster-than-light travel continue to inspire and challenge our understanding of what might be possible. These imaginative stories push the boundaries of our creativity and drive our curiosity about the universe, encouraging us to dream of a future where faster-than-light travel becomes a reality. Science fiction has had a profound influence on scientific thought, often inspiring scientists to explore new concepts and technologies. The imaginative scenarios depicted in sci-fi stories challenge researchers to think beyond current limitations and consider what might be possible in the future. The concept of space travel itself was heavily influenced by early science fiction writers like Jules Verne and H.G. Wells. Their stories about traveling to the moon and other planets sparked public interest and inspired early rocket scientists. Star Trek has had a significant impact on scientific thought, particularly in the fields of space exploration and technology. The series introduced concepts like the communicator, which inspired the development of mobile phones, and the tricorder, which influenced medical diagnostic devices. Arthur C. Clarke's vision of geostationary satellites in his novel The Fountains of Paradise led to the actual development and implementation of communication satellites. His ideas bridged the gap between fiction and practical engineering. Science fiction often explores the ethical implications of advanced technology, prompting scientists and ethicists to consider the societal impacts of their work. Stories about artificial intelligence, genetic engineering, and virtual reality raise important questions about the future of humanity. The idea of a space elevator, popularized in various sci-fi works, is now being seriously considered by engineers. This concept involves a tether extending from Earth to space, allowing for cost-effective transportation of materials and people. Isaac Asimov's 3 laws of robotics have influenced the field of robotics and artificial intelligence. These laws have become a foundational framework for discussions about robot ethics and the safe integration of robots into society. Sci-fi's depiction of advanced propulsion systems, like warp drives and wormholes, motivates physicists to explore the theoretical underpinnings of faster-than-light travel. While these concepts remain speculative, they drive research into the fundamental nature of spacetime and gravity. The portrayal of extraterrestrial life in science fiction has guided the search for life beyond Earth. Stories about alien civilizations encourage astrobiologists to consider what forms life might take and where it might be found. Science fiction has also inspired the development of new materials. Concepts like transparent aluminum from Star Trek have led researchers to explore the creation of materials with similar properties, pushing the boundaries of material science. The depiction of virtual reality and immersive simulations in sci-fi has influenced the development of VR technology. These stories showcase the potential applications of VR in gaming, education, and training, driving innovation in these fields. Science fiction often addresses the potential consequences of climate change and environmental degradation. These narratives highlight the importance of sustainability and environmental stewardship, influencing scientific research and policy. The exploration of human augmentation and cybernetics in sci-fi has inspired advancements in prosthetics and wearable technology. These stories challenge scientists to create devices that enhance human capabilities and improve quality of life.
Science fiction conventions and conferences provide a platform for interaction between scientists, engineers, and writers. These events foster collaboration and idea exchange, leading to new insights and innovations.
Ultimately, science fiction serves as a bridge between imagination and reality. It encourages scientists to dream big, explore the unknown, and push the boundaries of what is possible. The influence of sci-fi on scientific thought continues to drive progress and inspire the pursuit of knowledge. Science fiction often presents a vision of the future that, while imaginative and captivating, differs significantly from our current technological reality. Comparing fiction with reality highlights both the progress we have made and the challenges that remain. In fiction, faster-than-light travel is a common trope, with ships effortlessly zipping between stars. In reality, the speed of light remains an insurmountable barrier according to our current understanding of physics, and no practical method for superluminal travel has been developed. Sci-fi frequently depicts artificial gravity on spaceships, allowing characters to walk around as they would on Earth. In reality, creating artificial gravity is a significant challenge, typically addressed by rotating spacecraft to generate centrifugal force. The concept of teleportation is another sci-fi staple. While quantum teleportation of information has been demonstrated in laboratory settings, teleporting humans or objects remains firmly in the realm of fiction due to the vast complexities involved. Robotics in science fiction often features highly advanced, autonomous androids with human-like capabilities. While robotics has advanced significantly, creating robots with true general intelligence and the ability to seamlessly interact with humans is still a work in progress. In many sci-fi narratives, space is teeming with advanced alien civilizations. Despite extensive efforts in the search for extraterrestrial intelligence, SETI, we have yet to find conclusive evidence of other intelligent life forms in the universe. Energy weapons, such as lasers and phasers, are common in sci-fi. While laser technology has advanced, creating handheld or ship-mounted energy weapons with the capabilities seen in fiction is not yet feasible due to current power limitations and other technical challenges. Sci-fi often depicts advanced medical technologies, including instant healing and life extension. While medical science has made great strides, many of these capabilities remain aspirational, though research in regenerative medicine and anti-aging continues to advance. The idea of interplanetary or interstellar empires is a common theme in fiction. In reality, establishing even a sustainable human presence on Mars is a monumental task, requiring breakthroughs in life support, radiation protection, and other critical technologies. Virtual reality in sci-fi is often portrayed as indistinguishable from the real world. Modern VR technology, while impressive, still falls short of creating fully immersive experiences that engage all the senses at the level seen in fiction. Sci-fi frequently explores advanced forms of artificial intelligence with consciousness and emotions. While AI has made significant progress, creating machines with true self-awareness and emotional understanding remains a distant goal. Nanotechnology in fiction often features microscopic machines capable of performing complex tasks, including medical repairs at the cellular level. In reality, while nanotechnology is a growing field, we have yet to achieve the level of sophistication often depicted in sci-fi. Many sci-fi stories involve space habitats and colonies. While concepts for space habitats exist, such as O'Neill cylinders, we are still in the early stages of building and sustaining human life in space environments beyond low Earth orbit. Sci-fi often portrays instant communication across vast interstellar distances. In reality, communication remains limited by the speed of light, making real-time conversations between distant stars impossible with current technology. The comparison between science fiction and reality serves as both a reflection of our aspirations and a reminder of the challenges we face. While fiction inspires and motivates, turning these imaginative concepts into reality requires continued scientific and technological advancements. Public perception and enthusiasm for faster-than-light travel are overwhelmingly positive. The idea captivates the imagination and fuels a sense of wonder about the universe. Science fiction has played a significant role in shaping this enthusiasm. Movies, books, and TV shows depicting interstellar travel have inspired generations to dream about exploring the cosmos. Educational programs and documentaries about space exploration have also contributed to public interest. Shows like Cosmos and Nova make complex scientific concepts accessible and exciting, fostering a deeper appreciation for the possibilities of space travel. Public events, such as space launches and missions to the International Space Station, capture widespread attention. These events are celebrated milestones, igniting curiosity and excitement about humanity's potential to reach beyond our planet. Social media platforms amplify this enthusiasm, allowing people to share news, ideas, and dreams about space travel. Viral posts and discussions bring space exploration into everyday conversations, creating a global community of space enthusiasts. Crowdfunding campaigns for space-related projects demonstrate the public's willingness to support innovative ideas. Projects like Planetary Resources and Space.il have raised significant funds from ordinary people eager to be part of the space exploration journey. Interest in space tourism reflects the public's desire to experience space firsthand. Companies like SpaceX, Blue Origin, and Virgin Galactic are making headlines with their plans to offer commercial space flights, turning the dream of space travel into a tangible goal. Public perception is also influenced by the achievements of astronauts and space agencies. Figures like Neil Armstrong, Yuri Gagarin, and more recently, Elon Musk and Jeff Bezos have become symbols of human ingenuity and the spirit of exploration. STEM education initiatives aim to harness this enthusiasm to inspire the next generation of scientists, engineers, and explorers. By emphasizing the exciting possibilities of space travel, educators hope to motivate students to pursue careers in science and technology. Science fiction conventions and space-themed events provide platforms for enthusiasts to gather, share their passion, and learn from experts. These events often feature talks by astronauts, scientists, and science fiction writers, bridging the gap between fiction and reality. Museums and planetariums play a vital role in maintaining public interest. Exhibits about space missions, planetary science, and the search for extraterrestrial life provide interactive and educational experiences that engage visitors of all ages. The excitement around faster-than-light travel often translates into support for space agencies and their missions. Public backing can influence government funding decisions, ensuring continued investment in space exploration. Public enthusiasm also drives the media to cover space-related stories extensively. News about discoveries, missions, and technological advancements in space travel often captures headlines, keeping the topic in the public eye. The sense of collective achievement and global unity that space exploration fosters is another important aspect of public perception. The idea of humanity reaching beyond Earth resonates deeply, symbolizing progress and the potential for peaceful cooperation. Ultimately, public perception and enthusiasm are crucial for sustaining the momentum of space exploration. As interest and support continue to grow, the dream of faster-than-light travel remains a powerful motivator, driving scientific and technological advancements toward making this vision a reality. Bridging the gap between fiction and science involves leveraging the imaginative concepts from science fiction to inspire real-world scientific advancements. This relationship creates a dynamic feedback loop where each influences the other. Science fiction serves as a testing ground for ideas that challenge the boundaries of current scientific knowledge. By exploring the what-if scenarios, writers provide scientists with new ways of thinking about problems and solutions. Many technological innovations have their roots in science fiction. The communicator in Star Trek inspired the development of mobile phones, and the idea of the 3D printer was foreshadowed by the replicators on the same show. In the realm of space travel, concepts like the warp drive and wormholes, though currently theoretical, are studied seriously because of their detailed treatment in science fiction. These ideas push scientists to explore the limits of physics and space-time. The collaboration between scientists and science fiction writers can be incredibly fruitful. Writers bring creativity and a narrative that can inspire, while scientists bring technical expertise that can ground these ideas in reality. Public lectures and workshops often feature both scientists and science fiction authors discussing futuristic concepts. These events encourage cross-disciplinary dialogue and can lead to innovative thinking and new research directions. Educational programs that integrate science fiction into their curriculum help bridge the gap by showing students how imaginative thinking can lead to scientific discovery. This approach fosters both creativity and critical thinking skills. Media portrayals of scientists working on futuristic projects, like those seen in movies and television, help demystify the scientific process and make the pursuit of knowledge more relatable and exciting to the general public. Real-world projects that mirror science fiction concepts, such as space tourism or asteroid mining, demonstrate how fiction can become reality. These projects keep the public engaged and invested in the progress of scientific exploration. Advanced simulations and virtual reality technology are now being used to test concepts that once existed only in the pages of science fiction. These tools allow scientists to explore the feasibility of ideas in a controlled environment. The International Space University offers programs that blend science fiction with science fact, encouraging students to think boldly while grounding their ideas in scientific principles. This approach cultivates a new generation of innovative thinkers. Public competitions and challenges, such as NASA's Centennial Challenges, often draw inspiration from science fiction. These contests motivate inventors and researchers to turn speculative ideas into practical technologies. Popular science fiction can also guide public policy by highlighting the societal impacts of scientific advancements. Thoughtful narratives about the future encourage policymakers to consider ethical and long-term implications of new technologies. Science fiction conventions frequently feature panels on science and technology, drawing connections between the latest research and speculative storytelling. These panels provide a platform for scientists to discuss their work and its potential future applications. Ultimately, bridging the gap between fiction and science requires a willingness to explore the unknown and embrace creativity. By continuing to draw inspiration from science fiction, scientists and engineers can push the boundaries of what is possible, turning imaginative dreams into tangible realities. In this video, we embarked on a fascinating journey to explore the secret to faster-than-light travel. We began by delving into early theories of space travel, tracing the origins of our quest to break the cosmic speed limit. The development of relativity theory, particularly Einstein's groundbreaking work, set the stage for understanding the speed of light as a fundamental limit in our universe. We then explored the profound influence of science fiction on public imagination, highlighting how visionary stories have inspired generations of scientists and dreamers. This transition to modern scientific theories led us to examine special relativity, providing a detailed overview of how it governs the behavior of objects at high speeds and establishes the speed of light as a cosmic speed limit. Time dilation effects and length contraction, essential concepts within special relativity, were discussed to illustrate the bizarre yet fascinating nature of space and time at relativistic speeds. These phenomena have significant implications for the feasibility of faster-than-light travel, challenging our conventional understanding of movement through space. The introduction to general relativity expanded our discussion to the curvature of space-time, offering insights into how massive objects influence the fabric of the universe. This naturally led to the intriguing concept of Einstein-Rosen bridges or wormholes, and their theoretical feasibility as shortcuts through space-time. We examined the potential challenges and limitations of utilizing wormholes for faster-than-light travel, recognizing the immense energy requirements and stability issues that currently confound physicists. The Alcubierre drive concept was then introduced, offering a speculative yet mathematically intriguing model for achieving faster-than-light speeds through the manipulation of space-time. We discussed the energy requirements for a warp drive, underscoring the need for exotic matter and vast amounts of energy. Current research and developments in cosmology and advanced propulsion technologies were highlighted, showcasing the ongoing efforts of scientists to push the boundaries of what is possible. Criticisms and theoretical issues, including causality and time paradoxes, were addressed, providing a balanced perspective on the challenges and philosophical implications of faster-than-light travel. We also explored the properties and theoretical behavior of tachyons, hypothetical particles that could potentially enable superluminal speeds. The role of dark energy and dark matter in the universe's expansion was discussed, connecting these mysterious components to potential breakthroughs in faster-than-light travel. We examined NASA's warp drive research and the European Space Agency's initiatives, highlighting the innovative efforts of these leading space agencies. Finally, we considered the significant contributions of the private sector and academic research, recognizing how collaboration and public enthusiasm drive progress. The influence of science fiction on scientific thought was emphasized, illustrating how imaginative narratives continue to inspire real-world advancements. Thank you for joining us on this exploration of faster-than-light travel. If you enjoyed the video, please like and subscribe to our channel. Check out the rest of our videos for more fascinating insights into the wonders of space and the cutting-edge science shaping our future. Your support helps us continue to bring you the latest and most exciting developments in space exploration and beyond.